Okay, we are live on YouTube, by the way.
All right. Good morning, everybody.
Can you please check it?
Yeah, I will do.
Whoa! Look at Keros! Look at Keros' new look! Ah! Just put it on full screen. Ah! Come on, turn around, turn around.
Let me close the streaming first, and then whatever you want.
Okay.
Whatever you want.
Nice good look.
Is it the same link, Piotr?
No, that's a different thing. Wait, let me fix it.
He's a different person, don't trust him.
I have to fix
Because
the...
of the code or what? I meant to say.
He's Hero's brother.
I fixed it.
Evil twin.
He has no hair. Hero has hair. Long hair.
This is how you learn it.
No way! You cut your hair.
Whatever.
No, he's just his brother.
Evil twin.
Evil twin.
Yeah, evil twin, yeah.
He's barely red style.
Red, are you gonna do the icebreaker?
I could do that.
I think
No,
that
could.
happened.
What could?
I am doing it. Manage presentations. What do we have?
Let's see. On the first one we have Chair, Manthos, Arthur, and Runner, right?
Yes.
And then some lightnings. Red, did you receive the lightning addition?
Almost all, yeah.
Okay.
And YouTube works. If we're connected, can you say hi, everybody? Microphone test.
Hello, everyone.
Hello, hello.
Hello.
Good morning.
Hello. Who do we have here? Simon, Nicoleta, Milenko. Okay, you can warm up your hands, do your best drawings while we're waiting for more people to join. Nice. So beautiful. You can change colors, you can change tool, you can write text actually.
Well, I would say that last year the drawing skills were a bit better. Oh yeah.
Oh, boo. Okay,
Yeah, I was proposing to play. I was about to propose to play a game where you start on a whiteboard and you try to fill as much volume with your color as you can, but you're not supposed to touch any other color, any of the other participants. Okay, so you have to, once they cross, both of you lose. But seeing that now, I don't know if we can really play this game because there are some people that like to draw really all over the place, but maybe we can still give it a try.
Let's try. Let's try. I think I have a.
Just need an empty slide. Okay.
That's an empty slide. All right, guys.
So we just try to cover as much volume. So I think it's a good idea if you choose a different color.
Choose your color and fill as much as you can without touching the others. Okay, 3, 2, 1, go. Something like point by point. It's very, yeah. Oh, yeah, at least. Yeah. Put your space in the layers. Like impressionism. You see what the others are. You know?
Ah!
Ah, me lost.
What's that?
I think it was 50% filled. Can do better. Ooh. The thing is that we only see what you did after you release the mouse. So.
Ah, that's why.
Yeah. Me. Oh, this was a bad one. Only 30%.
Okay. So release the mouse more often. To be extra careful now. I did not practice, but I'm competing here with this. Okay, you just destroy everything in red.
Yeah, I don't know who is this red thing. Good.
Red is red. Here. Red, you are the red.
No.
Red is red.
No. All right. Gotcha. We got you.
So Mantos, for the next session, do we have all the slides?
No. Let me check for the one is. The last one is here in front of me. I can see it, but I didn't have the pitch.
A close test.
And let me check.
So we need the slides of
Bravo.
The first talk, Polaris.
Very good.
So Aditya.
The same as yesterday. I have to see if it
Yep.
changed.
I think I sent it today.
Yesterday. And I have to turn on.
Aditya said that have already sent them.
Then please send again.
Yep.
Did not receive. We also need talk number.
The last one.
OHP. The third one. OHP.
Okay. So Simon.
Nice. So, can someone tell me why Star Wars and not Star Trek?
Simon has sent the presentation. I'm forwarding to you.
You can let Montos talk, but you have to tell me why it was Star Wars and not
I sent it again.
Sorry. Go again?
Again?
Yeah, you said you didn't get my slides, right? I sent it again.
I got it, yeah.
Yeah.
We got it again. Oh, but without the attachment. We have it.
So it's good that we have this boot up session because we really need some time here to boot up.
Okay, people are drawing.
It was a long hangout last night. I think some of you left early, but then, later on it really took off and my God, that was a blast.
Amazing.
I mean, I would have not wanted to miss this.
Yeah. I mean, the satellite relay live, I mean, that was crazy. Yeah. Aha, gotcha. I mean, you were just saying that, boot up. It's pretty equilibrated today. I mean, that's there's a good balance of Star Trek and Star Wars fans. Some people making the bridges. That's the community. It's very good. So now, please today choose a very thin point and pinpoint where you are today, sitting today, not where you went on holidays, just where you are today. I don't want to know your favorite place. I just want to know where you are today. Hopefully, that's your favorite place. Cool, Morocco. I see. Where's that? Arab Emirates over there. Belgium, Italy, Atlantic. What is this? I think some of our friends on the East Coast are not woken up. Somebody on the far west, far east, sorry. Okay, good. Good. Too bad we can't zoom. A lot in Greece, some people in Russia. It's good. In Portugal or Spain over there. My point right now.
I'm sorry, I used the wrong size of.
I am Spain.
Dot.
I'm Spain. No.
Somebody from Luxembourg would have a problem.
There's an undo thing. Okay, found it.
Who's from Luxembourg? Who's sitting in Luxembourg?
No, just saying that somebody from Luxembourg would have a problem if they try to find their location.
Yeah. That's approximate. Right?
No problem, Luxembourg. Oh, okay. I was about to draw it on the map.
Oh, sorry.
Booms. Got it.
Good. The big point.
Perfect.
Somewhere there.
Very good. Testing stuff. Sorry. All right. Now is the time we test your microphone. So, where is it? Can you turn on your microphone, everybody? You say good morning, okay? You have to shout.
Good morning.
Good morning.
Everybody together. 2,
Good.
1.
Good
morning!
Microphone works. So,
Very good. We have
7 minutes to go.
yeah, we all have good energy, which we will need because it's gonna be quite some talks that we hear today, and we also will have 2 workshops running in parallel. So you have to later make a choice. And we have everything here now for session 1, but we're going to stick to the time so that we start at 11:20 UTC for those that just tune in at that time. And maybe you have realized that on the conference website, on the top you would see the current talk that is ongoing. Of course, this website, this Indico website, just takes this information from the timetable, and it is only as correct as we keep to the time. But so far, I think we did very well yesterday.
Can only remind for the lightning talks, it's 4 minutes. Every additional minute is 1 Bitcoin. So,
Do we have more opportunities for lighting talks?
We could take one more or two, depending on how much we want to eat on the next session, which is workshop and trainings.
Maybe next year we can give some space for on-the-fly lightning talks.
Yeah, the thing is that doing it remote is a bit complicated, but yeah, we have the workshop.
No, we shouldn't do it again remote. We said this is the last time. Yes.
Yeah. We have to do parallel sessions. We still have some room, you know. Like I'll be happy if I have one or more two lighting talks. So do not hesitate to reach out. Put it in the chat. We'll catch you. So if you have a topic you want to talk about, a new project, an open source tool you used and you want to share, I mean, it could be a topic about anything, obviously, and preferably open source, of course. And if you're starting your startup on an open source business model, we'll be happy to have it pitched as well. This is so nice. Do not hesitate to reach out if you have an idea, additional idea. We have 4 of them today. Correct. We have 4 of them. One is not mentioned in the timetable, but it's added. So we have in situ space debris detection, lean time management, MindaSat from Michael, and then we have another one from Michaelis, which is about SatStein. So do not hesitate if you have your own project you wanna share. Please say it in the chat, and I'll be happy to onboard you. Send me a title and your name. You have 4 minutes. If you want slides, send me the PDFs at the mail I'm putting in the chat. Read at bigboard.space. Right. Thank you, Matos. Matos, you are presenter now.
Yeah, we're starting. I know that I'm presenter. So, Aditya?
Yeah, sorry, I had some internet issues.
Okay. Are you gonna go with your camera off? Like, okay.
No, I'll switch it on.
Okay. So you can start, and Aditya is maintainer and the core contributor of Polaris project. Is AI and machine learning an open source enthusiast working on integrating AI with hardware. He was also participating in the Google Summer of Code with Libre Space Foundation, and today is going to tell us how we will go from a single satellite operator to a constellation with 1,000 satellites, and how AI is gonna help us do this. Okay, so Aditya.
Thanks, Manthos. So, as Manthos said, I'm going to talk about Polaris, about the visualization options which were recently introduced in our project, and how in for those of you who know, automatic machine open source is a set of automatic machine learning based open source tool to monitor the health of your like instead of
you're breaking a lot, so maybe you could turn off the video eventually, so at least we have the voice.
Yeah,
Right,
sure. Sorry.
Thanks. Matos, is it only me or?
No, he's breaking for me too, and also Juan said.
Okay.
I'm sorry.
minute setup.
Yeah, take your time.
We're having a microphone issue.
Also, the bandwidth shows very low for Aditya. I think he's reconnecting. Okay.
Moving seats. Maybe I can do the about Polaris, right? All right. Well, Aditya is starting. Maybe I just cover the slide. So I'm Red Bunga. I'm also like one of the maintainer of the Polaris project, so that's convenient. So this project aims at bringing automatic machine learning based open source tool to help operators manage their mission, to actually monitor and understand what's happening on spacecraft and when there is an anomaly. This is a global team working on it from Canada to India. We like to say it because when you're in the chat, you always have somebody who can answer your questions. So it's interesting, and it's supported now and part of the Remote Space Foundation, and it started as an idea from the open source Cubesat workshop in 2018. Okay, next slide. I'll just take printer. Aditya, tell me when you're in. So inside that tool, we use different other tools to tweak the machine learning. Yeah, Peter, heard you. And you can take it, Peter, too.
Yeah. Okay. No worries.
I'll finish that slide and then you go ahead. So there are different tools like XGBoost for extreme gradient boosting. It's an open source library. TensorFlow, it's an open source library to build neural network architectures. But then we also have the front end, which is based on React.js and 3JS for the 3D graph that we shown last year. Then we also use SatNox as our main data source, and also we use NOAA and SWPC for the space weather events. So because the tool is not just only on telemetry, it's also like making links with what's happening in space. So we could, the goal is to really explain the anomalies to the point as say, oh, there was a flare from the sun, so your spacecraft reacted that way. And we also use polyastro for providing orbits to understand where you are and what's your speed, etc. And maybe extract relevant input from that. And then on the next slide, Jan Peter will continue. You can turn on your camera, and we'll summarize what we did last year, present, and because this is a state of Polaris presentation. And Peter, if you're here, oh no, you're not here. You're disconnected. Okay, I will continue. Firefox crash. Okay, I'm okay. It's meant for me to be presenting that. Okay, thanks for preparing the slides, Aditya. Those are amazing. So what we presented last year is a Polaris generator dependency graph. That's this 3D view, which is based on a WebGL tool, based on 3JS. And what it means, so the nodes are telemetry measures, and the links are dependencies that are calculated thanks to machine learning. It permits us to find nonlinear dependencies, which you would not find with classical mathematical correlation. And we had a close collaboration with the Bobcat One team, with people inside the Polaris who joined the project to feedback and actually help a lot. We have a presentation here on the YouTube link. You can find on the presentation afterwards. So why did we build Polaris? So why Polaris? So Polaris is machine learning tool for operations. So first, there are many things, but the thing is that the main goal is that today you're managing one spacecraft, and eventually in the future you'll be an operator of hundreds of thousands of spacecraft, and you can't do that without a good artificial intelligence friend. That would be Polaris, hopefully. So we do that because we love to work with operators. That's good. We like to save time also to find the anomalies also, and we're trying to make it easy to set up so you can connect to your own data source for telemetry and get a good visual output for this. And why you should use that is because of all this, yeah. So, and it's also integrated. It's helping you integrate your telemetry with the space weather data and all the auxiliary information that is in space, not related directly. I mean, not from your spacecraft, external source of data. So, why are pictures so big? So, we have a simple command for robust visualization, so that you just do that command, so you don't have to find out how to do the visualization, because we have a fetch part which gets the data in a JSON form, and you just need your satellite ID number. We found that convenient from time to time, but happy to get your feedback on that. And then you have a learn command. So we're working on that. We're reworking that to get it more modular. But at the moment, you can learn the dependencies like that, only the dependencies for now. And you output a graph, which is also in JSON, that you can visualize thanks to Polaris base. Or if you want to detect the different behavior of your spacecraft and to display them, then you have a command which is Polaris behave. And you take the same output data from the fetch command, and you get a JSON. And this time you get a report, and finally the report is going to be more like our React.js full app, which is going to show everything, including the graph. But for now, there are two decorrelated tools at the moment. Aditya, I see you're back. It's amazing. How can we hear you?
Sorry about that.
Yeah, is it better?
Yeah, I might have soon after.
I don't hear it's better. Sorry.
You can continue.
Yeah. Okay. Okay. I will continue then. Jan Peter wanted to take it, but I don't see him. Okay, anomaly detection. So focus on anomaly detection visualization. So what we do for anomaly detection is that we order the data grouped by windows. So that's a classical approach when you wanna check different segments and different behavior in your telemetry in your spacecraft, and you don't know what is the breakpoints. We're actually trying to build a tool that detects those breakpoints between the behavior. So we have a neural network model, which is an autoencoder that tries to reproduce these windows of data. So it's reproducing the whole telemetry set on those windows. And as soon as there is an internal representation in this neural network that changes too much, we flag that as a big deviation. So there's a maximum local deviation. And for us, it's a behavioral breakpoint. Let's consider that such as a behavioral breakpoint. So a neural network watching all the telemetry kind of detects those breakpoints from, by incrementing in time like that. And what's happening is that we have the output to Polaris report on this interactive web page, and you could see the main statistics. So you could see like which telemetry impacts the most, the behavior analysis. And I'm not sure. I see what's over there. You could have like light and dark mode, but what's interesting is this graph of stacked telemetry. So the telemetries are normalized, and we separated positive and negative telemetry. Correct me if I'm wrong, Aditya. So that's why you have it seems like you have a reflection of graph, but on top you have the positive stacked telemetry, normalized telemetry, and the negative stacked telemetry on the bottom. It permits us to have some kind of a view of, if something different is happening, if you have like temperature rising at some point, you have a peak. Temperatures decreasing, you have a down peak. Those kind of things. And our tool actually detected breakpoints that we draw on this picture. You have some breakpoints that are in red lines. They're all in red lines, thin red lines. But you have like bigger breakpoints that are the breakpoints where the difference is big in the neural network internal representation. And we're trying to make sense of that at the moment. So we are discussing with the operators, trying to see, okay, what happened there, between there and there. At some point, it made sense. So we had like a lot of sense made with Bobcat one, for instance. At some other points, we don't know exactly. So that might be, you know, just a mistake. There is no really a behavioral change, but we can learn from that. Or something that happened and nobody's really aware of. So that's also interesting in that sense. Until what time do I have? Like, you know, have 10 more minutes? Oh, 2 minutes, I think. Mantos appeared. I don't hear you. Okay, visualization of Anomaly. Yeah.
You just passed the 12 minutes, but you can continue a bit more.
Okay, I'll make it quick, so I want the interaction to go on. So we have more visualization, like you can choose some telemetries once you know there's an issue. So you could see the stacked version. And then we could merge those plots of telemetries to see what they do. It's all in the report page. Well, in conclusion, what we want from you is that you try that tool. That would be amazing. So to get your feedback, pip install Polaris-ML, we're trying to release that quite often. At the moment, since the summer, we're trying to re-architecture everything. So that's a work in progress at the moment. But feel free to join us on the Polaris channel, and we'd love to have your feedback, features you love. If Polaris helps you in detecting anomalies and characterizing anomalies, and what didn't work so well. Yeah. And if you have questions, we're here to answer. We have this bunch of team. And we're trying to be always present at the open source Cubesat workshop. We have to, right?
So still on time. Yeah, still on time. So there is one question in the chat. It says Jean and asks if are you able to run and feed Polaris with real-time telemetry coming in?
Yeah. So at the moment we're not supporting streams. But we want to go there because the goal of supporting streams is that you could also be on board, you could move on board. Aditya did a super interesting study with Polytechnique Montréal on actually pruning neural networks. I mean, it was not correlated to Polaris, but that's something we could use. And meaning that we could achieve the same performances with less neurons, but that's not what it is, but it's pretty much that. So meaning that you have a smaller footprint, computing footprint, and therefore you could be on board. But real-time telemetry coming in, yeah, that's the thing. The thing is that what is real-time for a satellite is every time you have data dumps. Yeah. So I think you mean on board.
I have a question, and my question is: do you somehow share knowledge between satellites and subsystems, and do you have a way to, I don't know, to learn from one satellite and then transfer this knowledge on other satellites, or generalizing the knowledge?
Yeah. So we have this dependency graph where we have telemetry by telemetry. We want to add a semantic layer where we know which subsystem is holding that telemetry, so that we could actually learn that, you know, heating subsystem is doing that, or the battery is doing that. And if you have the battery of the same brand, actually we could eventually, we're trying to do that. We could see the signature of that battery, you know, power consumption, current fluctuation, all those kind of things, and detect that you actually have the same kind of battery, and eventually like confirm that with the operators or the system engineers, and then trying to learn, you know, for what happened on that battery on this other spacecraft, on that other spacecraft. This is something we'd love to do. Since you know, many of the subsystems are reused here and there, so I think we believe we can do that.
To add on to, sorry. to add on to what Red was saying, one more thing is that the dependency graphs allows you to find out these relationships between subsystems. So if you are using, say, the same kind of battery and your power system board or something, you can essentially find a relation between those, and you have a model for the whole subsystem as a subgraph in Polaris. So yeah, it will be very valuable to extract that as well.
Okay, so you can even detect an anomaly that this kind of this specific battery is not working as supposed to, as the other batteries of its kind.
Yeah.
Yes.
So
Okay.
for that, what we did was during a proposal which we submitted, we found out these breakpoints, found out the dependency graph before and after the breakpoint. So when you compare these two graphs, you kind of have an understanding of how the relation between subsystems are changing, and that will kind of tell you what is underperforming or overperforming, or what's giving you the issues. So for example, the satellite we analyzed, there was some thermal issues which are happening, which was kind of related to the power budget or something. So that was a interesting insight which we got just by doing an automatic analysis.
Okay.
I think we're not too far to be able to. I mean, we'd love to say if you to do some prognostic, like if you continue to use your spacecraft like that, the battery current is going to fail or something. So because we learn from the anomalies from others, that would be fun. And using SatNox is amazing because we've seen yesterday 700 missions. We don't have the decoders for all of them, but that's a lot of matter to learn from.
Cool. So have you used any of those data to train any system already?
Yeah, we have trained on.
Go on.
We have trained on LightSail 2 as well as Bobcat 1 and Orsat. So these are the three major satellites, and we had done a preliminary analysis on Cubic as well before the launch.
Okay.
Yeah, and the advantage of Polaris is you only need the decoder to be present in SatNox. That's all you need. You can just integrate it with Polaris. There's a parameter, like if you want to give the actual values of your parameters to Polaris, you just need to create a normalizer file. If you don't want that, there's an option to skip the normalizer. So if you have everything set up for SatNox already, you can just plug Polaris into your workflow and just test it out using just one command. So.
Yeah, it's true.
Awesome.
For if you we got requests from people in bigger companies with bigger spacecraft, and we also manage a way to input a CSV file, so we're not connected to their database because it's too custom made, and you can always do differently, not just in SatNox. SatNox is covered. It's cool.
Cool. Do you have in mind to integrating any CCSDS protocol in order to connect in this kind of database and streams and more? I don't know.
Yeah. Why not? I mean, that's in the pipe. We need more people.
Yeah. More hands. Yeah. Ironically, Aditya's microphone started to working perfectly after the presentation, so I don't know what's happening. Someone makes fun of you, I don't know. So, thank you Aditya, thank you Red, and Aditya again, his internet is down, no? Okay,
thank you.
We thank you, and we call George Vardakis.
Hello, can you hear me?
Hello, yes, we can. So, are you ready?
Yes, I am.
Okay. So, George is a member of Libre Space Foundation, mainly working on DSP and embedded systems, and he is involved in a number of projects in LSF. He has involved in Cubesat, in SDR Makerspace, and now lately in Cubic. Implementing CCSDS and Space Data Link Protocol on Cubics. So he's gonna talk about this, I suppose, yes?
Yeah.
Okay, so you're yours.
Thanks, Marcos. So yeah, my name is George Vardakis, and I'm going to present to you our project, a LibreSpace project called Open Space Data Link Protocol, which is an implementation of the CCSDS telemetry and telecommand data link directives. So we're going to speak a bit about how it started, say a few words about the CCSDS TM and TC directives, about our implementation, some things and some architectural choices that we made. We're going to speak a bit about the software that we implemented in order to operate the OSLP instance, and also some next steps for the future. So basically, it all started last year with the development of Cubic 1 and Cubic 2. We basically were in need of a MAC layer protocol in order to have a reliable channel for our telecommands, basically. And the CCSDS directives were a perfect fit for that, not only because they provided all the functionality that we needed, but also because we at LibreSpace Foundation, we love standardization and the CCSDS in particular. But the issue was that at the time, and to our knowledge, there wasn't an open source implementation available which would be suitable for an embedded system, for embedded devices like our own. So we thought, let's go ahead and implement it ourselves. Now this is a picture showing where the data link protocol lies in the OSI stack. So you can see that in the data link layer, we have two parts. The lower part is the synchronization and channel coding sublayer, which takes care of all the channel coding, the synchronization, basically everything that's needed to transmit in a noisy channel. And in the upper layer, we have the data link protocol, where all the framing happens and the retransmissions and frame control, flow control, and all that. So the space data link protocol is comprised of a number of different protocols. So these are depicted here in this tree view. So we have the telecommand space data link protocol, the telemetry, the advanced orbital system space data link protocol, which that part we did not implement. And there is also a separate document, a separate protocol named Communications Operation Procedure, which basically describes all the functionality for the ARQs, for the automatic repeat request, the flow control, basically the acknowledgement mechanism that is applied only to the telecommand part. So let's see some more things about these protocols. The features that they provide, some of the features are segmentation and blocking of packets. They provide a mechanism for channel sharing, so how to segment the one channel in more and basically assign a different channel to different applications that you may have on board. And that way provide also different quality of service requirements per application. They describe an automatic repeat request and the flow control mechanism, as we said, that is defined in the Communications Operation Procedure 1, the COP1. This is only applied to the telecommand part of the protocol, so you can only have retransmissions for the telecommands, not basically for the telecommands that you send from the ground station, not from the spacecraft side. And also a feedback channel is described. For that reason, they use a specific data unit called the CLCW. Also, we have an optional security protocol that is described, and the advanced orbiting systems protocol is basically an extension of the telemetry part. It provides some extra services, and the difference to the rest of the protocols is that the rest of the protocols are unidirectional. So in a communications link, each end of the communication link must run a different protocol. And usually what happens is that on the ground station, we usually run the telecommand space SDLP, and on the spacecraft side, we use the telemetry part. You cannot use both of them in both links, one of them in both links, for example. But in the case of the AOS, you can use it in both ends, so it's bidirectional. That's the difference to the rest of the protocols. But as we said, we haven't implemented that. We didn't have the time. Another interesting feature that is described is the channel sharing that we said. And in this picture, we can see the different layers of the channels that CCSDA describes. So in the lower layer, we can see the physical channel. The physical channel basically is the air or the absence of it in space. And the CCSDA protocols say that that there may be multiple physical channels because each direction in a communications link is referred to as a separate channel. So the ground to space link is one physical channel. The space to ground is a different physical channel per CCSDA directives. And also you can have different physical channels if you have, for example, different communication frequencies with one specific spacecraft. Now on the physical channel, you can see that we can have many master channels that are multiplexed. Now each master channel is assigned to a different spacecraft. So each spacecraft has one master channel. And there we can have multiple virtual channels. So multiple virtual channels are multiplexed onto the master channel. Now, each virtual channel, as we said, can be assigned to a different application on board. For example, in Cubic, we had a different virtual channel for managing different stuff on the spacecraft. We have a different virtual channel for the experiment, for commanding the experiment on board, and so on. And last, only for the telecommand part of the protocol, you can further segment the virtual channel into multiplexer access points, MAP channels, as they're called, if for some reason you want to have more streams of data from the spacecraft. And all this is done in order to facilitate having different quality of service requirements per virtual channel or per map channel. So you can instruct, for example, one channel to conform to the ARQ. So one virtual channel can have retransmissions, another one may not have retransmissions, or you can have different priorities per channel. Now, a few things about our implementation. Basically, what we needed was a library in C or C++, which would be suitable for running on an embedded device. So it preferably would have low memory utilization because the resources are limited. So we basically wanted the user to have as much control over the memory utilization as possible. So what we decided was to go with a platform-independent, OS-independent implementation of the library, which would be capable of running on any operating system or even bare metal. And furthermore, it would give all the structures that are inside, are used by the library, would be provided by the user. So basically all the queues, the different queues that are holding packets into different phases of the protocol, they are provided and managed by the user. So the way we did that was, as you can see in the right of the picture, we used the weak attribute of the GCC. So we defined a number of functions that we used inside our code base, and then the user has to go and implement them in their own code base. So most of the features that are described in the directives are implemented in the OSDLP library. We have the TCTM and the COP in separate files. As we said, the user implements and manages the various queues. Of course, this requires more effort by the user because they have to implement some functions, but it gives greater control to them, which is very important in such systems. And also, the user has to implement the timers, any timers that are needed, also any locking that may be needed. And we also have some unit tests inside the code for testing a number of scenarios. We also had a contribution in our repository of the Space Packet Protocol, which is a network layer protocol and is suitable also for onboard communication links apart from the usual ground to space, space to ground, and space to space. And we also implemented, because we wanted to control our satellite and the OSDLP instance running on there, we implemented a very simple CLI program in C++ called OSDLP operator, through which we can initialize the protocol, we can transmit the telecommands and receive the telemetry and decode them. It uses UDP packets to communicate with the RF frontend, and it's very easily configurable through just one file using the libconfig library. Now, some next steps are refactoring and improving the usability of the code because it was developed in a very short time frame, so there is much room for improvement over there. Of course, we need to work on the documentation part because now we only have some comments, Doxygen style in the header files. More testing is, of course, always a good thing, and also implementing the AOS features or the Space Data Link Security Protocol would be also very nice. Here I have some references to all the various documents that I mentioned in the presentation. And at the end also we have the repositories holding the OSDLP and the OSDLP operator. And if you have any questions, I'll be glad to answer. Thanks. Manthos, I can hear you.
Yeah, I was muted. Yeah. Thank you, George. So I think there are some people typing, but I have a question, and is how do you think a small satellite and a small satellite mission can take advantage of this, and why should use it? Do you have any?
Well, I think it all comes down to the benefits of standardization. So if you have a CCSDS protocol on board, then we have seen, I think, how easy it is, for example, for a network like SatNogs to very quickly and easily convey all the information, to the operators of the satellite or even the community. I mean, you can just write a decoder that you have on the SatNogs network, for example, and everything gets decoded instantly without having to go through a lengthy communication phase with the team that's running the satellite and to coordinate about the structure of the frames and all that. So everything is ready over there. And there are also other aspects, like, for example, you can use some open source frameworks that are available for operating satellites, like the OpenMCT or YAMX, and basically you can use them out of the box with a satellite that's using the CCSDS. So yeah, there are many aspects.
I have
okay,
a
there's
question.
a new question. Yes.
I posted it, yeah. That are you considering to add the Unified Space Data Link Protocol (USDLP), which is basically a generic version that can be used for the TC and the TM frames?
Okay. We haven't thought about that, but we are open to suggestions as to what basically is useful for the community to add. So yeah, sure, full on. But the thing right now is that we are kind of limited in people that can work on that. So any contribution from the community would be greatly appreciated.
Milenko has already raised his hand for contributions.
He is there, yeah. Thank you for the space packet protocol.
So Vitos asks, on which platform have you tested it from the on-board perspective? So
It was on the Cubic mission. It was tested. Yeah, I don't know if you want any more details about the platform itself.
Yes, if you want to go a bit about the hardware.
Yeah, if you want some info on the hardware, Matos can answer, I suppose.
If you like, you can go on and tell that, like the processor and yeah.
The processor, I think it was an STM32. I don't remember the exact model. L4, I think. I don't remember the exact model.
Yes, Elias says yes.
Yeah.
And also Manuel said, and what about the front end?
What did he say? Sorry.
And what about the front end of the
The front end, which was it? It was the AX.
Can't remember, but maybe Manuel or Elias.
5043. 5043.
And yeah, and how this can be used for multiple satellites? How do you this is scalable in order to?
So the documents do describe how to use multiple satellites. Basically, it all happens through the addressing and the different channels that I mentioned also in the presentation. At the beginning, it was not supported by the OSDLP because, as I said, we developed it in a very short time frame, so we were only focused on the cubic. So we didn't integrate support for multiple, easy support at least for multiple satellites. But lately we have been working on integrating this functionality to the library, and in the OSDLP right now you can use it for multiple satellites. Only the operator, only the OSDLP operator does not implement it yet, but it is also planned to support in the future.
Okay, so thank you very much.
Thank you.
And Manuel also sent a link. You can check. Okay, thank you. And Simon, are you around?
Yes, I'm here.
Okay.
I can switch on my camera as well.
Okay. The channel has a bit noise, I think.
Could be.
Yeah, it's a bit noisy, like static noise.
Also, the slides have a bit of noise, at least
Yeah.
for me. Okay, now it's better. I loaded the other one.
Yeah, I think also now the sounds better.
It's better now.
Yeah, it's okay. I think it's okay. Okay, so Simon is a system engineer in OHB Hellas, means OHB in Greece, and responsible for technical developments on next generation on-board computer architecture and high performance on-board processing. He has received a diploma in electrical computer engineering from the NTUA, the National Technical University in Athens, in 2016, and he has worked from 2017 to 2021 as an FPGA hardware designer for avionics systems in the Institute of Space Systems of the German Aerospace Center in DLR in Bremen, focusing on the development of distributed scalable onboard computers for space avionics. So, and today he's gonna talk to us about how in OHB in Greece they try to develop the next generation for onboard processing for satellites. Okay, so Simon, the stage is yours.
Santos. Yeah, I want to give you today the approach of onboard data processing and open source on onboard data processing from the perspective of an OHB-LS. So a person to you that don't know it, it's Germany's Technology and Space Corporation, and it's an independent company in the aerospace sector that is major space companies in Europe alongside Airbus and Thales. And there's activities in range, not just space systems, but also aerospace with launchers and digital services, which is the newest of the three pillars. And as you can see here in the slide, there's many subsidiaries over Europe, one of which is also OHB-LS. OHB-LS is one of the newest ones. We were founded in 2018 in Greece. We're fully owned by OHB-SE in Germany, and the establishment followed back then MOU between OHB and the General Secretariat of Telecommunications and Post. Our main activities on the technology domain are mainly on the high performance data processing and AI on board. So that's something that we decided to do in Greece for very good reasons. I won't go into details now. I'll mention some things later on. And regarding the space missions, I also want to talk a bit about satellite as a service, which is one of our visions in Greece, and where open source comes into play a lot. Let's say some words now about why open source, and why open source from the perspective of a company like OHB. And there is a need for open source in Europe. My view and our view is that it's mainly not just limited to, but two important pillars are the new space approach that requires moving away from the traditional approaches and the way we've been building satellites in the past. And another reason is a push in Europe towards technology independence, where open source can play an enabling role in new developments. And of course, in order to achieve those, we need a community-based approach in the developments. And that's something that's well understood in Europe and in space, but maybe not so much in the big industrial groups like OHB, which are a bit catching up on that, but they can't avoid it, I believe. And I can give you our perspective on onboard data processing, which is our main activity here in Greece, where we can see that we have many technologies that we use for the developments we do onboard payload processing, and we use software, for example, the partitioning that is open source. Jailhouse is a very good example that we are using, and we're aiming to use also in the future. And we can also see that RISC-V is something that has reached space, and there are developments that are also being traditional providers of space hardware like Cobham Geisler and Microsemi. This open source approach is not just related to shift in the space domain. So needs in the next generation data handling systems. So the two main needs we can see is one regarding flexibility, move away from using one big chunk of hardware, but rather use smaller modular blocks, so building blocks in order to build one big onboard computer with mixed criticality, of course, since we do want evidence that COTS is being increasingly used also by big companies, targeting. And on the software side, we do want to have a system that's easy to program, of course, and testing is a big role on that end, and we want to have frameworks that we can reuse, and they're easier to access from a bigger pool of developers. And that is very evident and something that is already knocking on our doors since some years. It's the need for increased performance on board. So we can see that new satellites and new missions generate a huge amount. Processing is nowadays unavoidable. There's no way around it, basically. And we can see that also AI is playing an increasing role in onboard data processing, where big companies also have been more reluctant way, but even there you can see that there are developments that show that it will be used, and it will be used more and more. And in that regard, we can see that going from the ground to transferring it, processing in space, so we have a type of cloud-based processing, is something that would also see in applications like the App Store, so applications on board. I would say some words.
Simon, there is some chopping on your line on your voice. Do you want to try to shut the camera?
Yes.
Go on.
Can you hear me now?
I think yes, yeah.
All right, perfect. Exactly. So, satellite as a service. Let me see one moment. Exactly. So, satellite as a service. That's one of the reasons I believe the flexible onboard processing change, and it is being enabled by the reconfigure implementations as well as the whole cloud service approach. It's something that will have a big change in the way we offer services in satellite services. That's quite evident, but it's basically renting out easy access to what we call. And our view and our vision on that is that it will be a platform. So it's something that is open to contributions from other people, and where any kind of satellite can potentially, let's say OHB offers a satellite as a service, it will be also open to list satellites provided or other satellite as a service products. And this, in our economy, and of course maximizes the resources in orbit, that is will have to be answered in the future with all the new developments and all the new satellites that OHB Hellas has decided to implement the satellite as a service because there is a real need to do this in Greece. Decided out of the blue. It is obviously a service that's as a new type of service for Europe, and not just Europe, mainly, but not just nations, also institutionals. And our goal is to rely and develop and the satellite as based on existing developments in Greece, closely with partners in Greece, and also together with open source activities in Greece. So we have a good Libre Space Foundation, and we do have a good and that are the ones actually that did show us the need for an open source approach. I think that it has been, as you can see here on the right, in the nice overview of the proposed satellite as a service approach, the hardware and software on board the satellite, and that connected to the ground through a distributed ground network. So that's also an approach that will be from the ground, targeting this approach. So it's not just onboard processing on its own. It's something that we all in all believe that will benefit not just OHB as a company and the space sector, but also Greece in general. Right, I would like to go into much more details. It was a quick overview. Leaves a lot of room for further discussions, also on the companies, because I think that's something that is changing just in Europe. So if you have any questions, or I think during the break later on, we can also have a more in-depth conversation if anyone has any questions on the presented information now here. Questions, please feel free to ask me.
Thank you.
Can you hear me? So thank you, Simon. Thank you very much. There is already a question in the chat, and Arthur, do you want to put it?
Yeah, I'm wondering if OHB is somehow involved or observes or follows the SAWAR activity, which is I think is a CNES-led activity to define the an onboard reference architecture for satellites.
It's a CNES activity for defining onboard processing is mentioned.
Yeah, I wonder if OHB
SAWAR.
SAWAR, yeah.
Yes, we have OHB has not have a big involvement in SAWAR, but we are following. So what is interesting for us is the ADA, that's data handling architecture for the standardization. We are closely following this.
Okay, I didn't catch the name. Can you please repeat?
Yes, I can.
Or write it in the chat. Yeah.
Yes, it's the. But we have, as a company, as OHB are involved in there, and OHB, as OHB Hellas, we started in it.
Thanks.
Jean has one more question and says, was the existing open source community in Greece, in parentheses LSF, a reason to set up this business there?
To that, I would say that when OHB Hellas was formed in 2008, in this case, and the business was to for Greece and for OHB and for OHB, the way that the company deploys its subsidiaries in Europe, it's an organic way. So we has a competence that is supporting the activities of the group, and it's something that you can build upon existing know-how and competence in the country. And we saw that onboard or that is advanced in Greece, and So we started working on that, and that's something that we starting then from 2018 is building up on partnerships and understanding actually the ecosystem in the country. And there we did we have a very good understanding, and that has influenced a lot the open source, I would say.
Do you want to repeat your last sentence, because I think we lost you?
Yes, I said that our approach, it has been influenced, of course, a lot by our partners. After several discussions, we did realize that it is something that is important for our developments, but it's also something that done in Greece, and there's extensive know-how in.
Okay, I think that we lost only the last thing. Can you hear us?
Yes, I can hear you.
Okay. So yeah, I also have a question. Do you think that this can be led to a paradigm shift, because traditional space is very closed, and the big corporation space, they are like not only they're not knowing, but they're a bit against open source because probably of the defense background. Do you think that like the new space is a paradigm shift and gonna lead towards open source for big companies too?
Our view on that is that it will lead to a paradigm shift, of course, and it's you can see that in the way that the new space is drawing small companies and activities. And for example, the satellite as a service is a service that has followed similar approaches on terrestrial applications, so Airbnb or Google applications, etc. This shift. The thing is that space in general, even though it's considered as the frontier of technological development, it's very often catching up to the activities on ground, and the big companies are reluctant to change, but it will happen.
Okay, I also agree with you. Okay, so thank you very much.
You're welcome.
Okay, so we'll proceed with the next talk. Julian or Julien?
Hello. Yes.
You are. So it's Julien. Okay.
Yes.
So you can share your camera, and
Yes.
Arthur already load your slides. So welcome, and Julien is an engineering student at the ISAE Supaero, interested in space systems and software development, worked on the LLink project during the internship with Thibault, and he's currently on his gap year studying control theory in Moscow. And he's gonna tell us how the modern web technologies can be used to create software tools for Cubesat mission design. So, the stage is yours. Thank you.
Thank you for the introduction, Montos. So I'm really glad to be here. And yes, so I will be talking about this project, LLink. I took part in this project during an internship with Thibault Gatto, as it was told. And the idea behind this project is to use modern web technologies for link budget calculation. So, first of all, this project starts with Nanostar project. This is a result of the cooperation of multiple European actors. And the idea is to have a set of tools, open source tools for student projects for nanosat development. And one of these tools is GSAT-orb. It was developed at ISAE Supaero, and the goal was to add link budget calculation capabilities to this tool. So about link budgets, really quickly, the idea behind the link budget is to take into account all the links, all the gains and losses along a transmission path. And since there can be many of them, the use of tools is really helpful to take all of them into account. So some of the available tools, for instance, there are multiple calculators for link budget online. They can be really useful, but they are a bit simple for some use cases. There is also another tool which is a predecessor from GSat, which is called SatStein. And the issue with this tool is that it's not open source. Otherwise, it's a great piece of software because it is used for educational purposes, which is what interests us with LLink. There is also the Orsat spreadsheet, a great tool because it is quite comprehensive and you also have a lot of documentation to help understand. So for student projects, great tool. And out there are also Python libraries that are able to do link budget calculation, dynamic link budget calculation even. And so we wanted to use those libraries within our project to build upon in order to have an ergonomic tool for link budget calculation. So we use the Python link predict with the link just below, which I recommend you check it out if you don't know about it because it's well documented. Really interesting to use. So the first step was to build our standalone project. Here is a really basic overview of the project. The idea is that the user connects with his web browser to our application, and the application then handles all communication with the API and the Python libraries in order to do link budget calculation. So here is a quick look at what the application looks like. On the middle, you have this part where you can tweak some values for your link budget. You have a part with documentation. You can also see some quick results on the right. So about the technologies that were used for this project, I will be talking a bit about the web framework, about web application framework, especially Angular, since this is the one we used. Angular relies on TypeScript. TypeScript is a superset of JavaScript. This is basically JavaScript with some typing capabilities and other stuff also. It's a really great language, really interesting, nice to work with. And so the question that arises is, why would we need to use a web application framework? Well, the idea with web application framework is to have a faster development process because they provide all the boilerplate code that we need. There are built-in capabilities for form handling, for instance, inside Angular. You also have a lot of tools that help us build an optimized application. And there are many different web application frameworks like Vue.js or React.js, which we heard from a bit earlier. And all of them have in common this paradigm that in an application, everything is a component. And this is a really interesting thing because it means that the concerns are really well separated and that these components can be reused independently. So the reason we stick with Angular for LLink is that it was already used inside GSat, so it made more sense if we wanted to integrate our project to keep working with Angular. Which leads us to, so this part about components, this leads us to the single page application concept. On classical websites, when you click a link, you will load a new web page. But on a web application, what happens is that since everything is a component, what you need is only to load the components that you don't already have. and you can reuse those that are already used. And this is interesting for two main reasons, because this leads to a more coherent navigation experience. You don't need to reload the whole page, but also you have some faster loading times while using the application. The only downside being that you lose a bit of, it's a bit slower at the first start. Also, thanks to Angular, we are able to generate these test reports just here. So these are some unit tests that were written for the application. We also have some Docker containers available on GitLab if you want to test it out. And another important part of this project was the ergonomy. Well, I am not a user experience designer, but with this project, I still had to deal with some issues, some kind of issues related to user experience. And what was really interesting and important was to make sure to avoid any user frustration or making our interface confusing. So basically, our application, it's a big form where the user has to input a lot of information, and then we can transmit it to the libraries. Well, it can seem simple, but in fact, there are entire books dedicated to forms. So it's not that straightforward. Just as an example, here we have an example. If we want the user to input units, how do we do it? We can think of using drop-downs. We can think of laying out all the different possibilities side by side. The issue with the drop-down is that you need one more click. One more click doesn't seem much compared to the alternative, but since the user has to input dozens and dozens of fields, it can become a bit frustrating. But on the other side, the alternative, if you have a lot of units, the interface quickly becomes cluttered. So there is always some kind of compromise to find in order to have an accessible application and to avoid all ambiguity. Once we had this first part of the application, the idea was to integrate it inside the GSAT. It was our first goal. Thanks to how we had components, we could just put them inside modules in order to create an Angular library. So this is almost the same graph as before, only that now you have this library component. And what this means is that you can simply use any Angular application, load the library here on the left in blue, and you can use this library contains all the necessary components. And this means that in any Angular application, you can import LLink and start using it. So I wanted to show you a small demonstration. Okay. I think it works. So, just to see.
Yes, it works.
Great. So here is GSAT. You have a cesium visualization here with satellites moving in real time. We import our project, go to LLink, where we can choose a satellite to work with, import data, and then we can trick our values regarding links. Here we're changing the frequency of the uplink. We can compute. Everything is sent to the backend. We see that here our requirements of 10 dB are not fulfilled. So we increase the transmitter power, compute again, get our results. And then, of course, we can export our results to be used later. We can also save the whole project if we want to work again later. So this was to show you some sort of typical use case of this project and have a better idea of what it looks like. Okay, back to the presentation. So, okay, here are some backup slides. So if we want to draw a conclusion from all of this, well, the idea was to show how web technologies could be useful for such engineering problems, for such projects. And we've also seen how easy it was to interface together multiple tools, from Python LLink Predict to GSAT. So LLink was a bit like a project in between. And I think that it would be really interesting to see what could be done with other issues, other problems. And yesterday we had a great talk about docs, which has has the same problematics as Nanostar and GSAT in part. So maybe it would be interesting to see some kind of collaboration. Thank you very much for your time and for your attention.
Thank you, Julian. Thank you very much for your presentation. The links that you have over there, you also hosting the app, the application, or is also only the code in the links?
We tried hosting the application, but we weren't successful because of at first we wanted to host it on the Israeli Superheroes infrastructure, but we had some issues with VPNs and such things. So there still are the Docker files that are available, the Docker images that are available on the GitLab project.
Okay. Thank you. So there are questions, 3 already. The first one is from I don't know how to pronounce this. Possible to adapt /extend simulator to optical links?
Well, since it is built around a library, a Python library for backend, well, in theory, it is possible to add optical links, but it wasn't really the use case when we built it. So we might need some adjustments in order to make it work for optical links.
Okay, and the second question from Arthur: how complex was to get graphics working in Angular and animation over static? Yeah.
Oh, I think we're talking about the moving graphs. So for this, if I go back to the different tools used, this is done using div3.js. Here it is. div3.js, which handles SVGs, vector graphics, using JavaScript. So let's say that it wasn't easy, but once it started working, it was fine. It took some time, some fine tweaking, trying different solutions. But in the end, I think this part is clean enough.
Okay. And another question, just got in by Zem. How do you take into account different location on map / different beams, etc.? Okay.
I think we are talking about GSAT, the visualization, zip thing maybe. So this is done using Cesium, which is open source software. The idea is that, okay, with regards to calculation, all right. Okay, so the way it is handled is that the position is not taken into account. What is taken into account is the distance between both antennas, the height of the station, of the current station, and it doesn't depend on the position on the globe.
Do you take atmospheric losses and other like misalignment of the satellite and the antenna in account?
Yes, so it is handled by the backend, by the Python library, and since there was already this possibility, we added the different losses, atmospheric losses, misalignment. They were already available, so we just had to add a field, make sure everything worked fine. So yes, these are taken into account. The model is simple. It's a simple model where you have to give your own losses. Maybe it could be how to say it, improved by requiring less thought from the user. But for now, you can choose some loss, some security margin.
Okay. And do you describe somehow the antenna radiation pattern, or is?
Well, there was this. I tried just to have at first some antenna patterns, but this part was a bit complicated. So in the end, we didn't add antenna pattern, but it would be really doable to import into the application an antenna pattern that would be transmitted to the Python libraries. There was an attempt, but it didn't succeed in the end.
Okay, so more hands are needed, yes?
Exactly.
Okay. So another questions? I can't see. Okay. Just appeared one. Arthur, it appears that the LLink could be framework for other backend libraries, e.g. thermal analysis, etc. Do you consider to make LLink more generic to use for such cases? Interesting question.
Well, yeah, really interesting question. It hadn't been, we haven't thought really much about adapting it to other cases, but I think that this approach might be adapted to other cases, thermal analysis and others. So maybe there is something to look at in this direction and think about making it more generic. I think it would be a great thing to have something more generic, to be just more modular, more robust. But this hasn't been done already.
Okay, I want to add the power budget option too. Which is critical for missions, especially for small missions. Okay, thank you very much. Thank you for your presentation. So, Elias is here. Okay, so Elias' presentation is loaded, and Elias is an LSF contributor that does a bit of electronics, bit of software, bit of mechanical, and working on a lot of LSF projects in Cubic, SatNox.com, Seedlock, SatNox, whatever is around. So can you hear me from his microphone too, I think? Because I hear my voice. So he's gonna talk about Cubic. I'm closing my microphone.
Okay, so there was some echo there. Hello, everyone. So in this presentation, we're gonna talk about Cubic, and we're gonna focus on the architecture and the development process that we followed for this mission. So a quick overview of what is the Cubic mission. Cubic mission is an experiment for attempting to solve the problem that occurred during early operations of a satellite launch, where the satellites cannot be easily distinguished and tracked by radars due to the fact that they are either too small or there are too many together. So in order to try to identify the satellites, we try to use some standard techniques, which is transmit a beacon and an ID for this beacon, and this will uniquely identify that a specific satellite is alive, and then there's the matter of actually tracking the orbit of this satellite. And if this satellite does not provide any information about its position, the orbit usually is tracked by a radar. And in this experiment, using various modulations and by exploiting the beacon preamble and post-able or residual carrier. We try to extract orbital information based on the Doppler shift that occurs as the satellites crosses the sky. So that's basically the experiment that the cubic satellites are going to conduct. These are the cubic satellites, Cubic 1 and Cubic 2. It is a fully open source project, and it was developed using open source tools. On the right, there's a photo of the two assembled models ready to be shipped for flight. And on the left, there's a mechanical model made in FreeCAD and then in Blender for beautification. So the actual satellite is quite a simple system. As you can see, there are 5 solar harvesters for providing power to the satellite. Each one of them has a maximum power point tracking mechanism for optimal exploitation of the sun power. All these are connected to the power management system, which provides power to the rest of the satellite, and also has an onboard battery management and monitor chip that provides quite extensive information on the battery status, either charging or discharging, and actually it does prediction of the time that is left based on the consumption that the satellite uses. And finally, the heart of the satellite is the comms board. The comms board, it has been presented many times in the past, so it's a quite powerful comms board that can also act as an OBC. And this is the case in this mission, because not only it handles the transmission and the experimental part of the mission, but also handles all the operational aspects. On the software side, there was a driver for AX5043 transceiver implemented. There is a telemetry telecommand, of course. Everything is controlled by a finite state machine. We also included the OSLP project, which was presented, I think, 2 presentations before this one. And there's also a driver for the power monitor system and an entire set of ground station telecommand software, which we'll see shortly. So during deployment, once the satellites are actually thrown out of the deployer in space, there is the finite state machines handles the post-deployment operation, and this requires a 30-minute hold of time, so for the satellites to have the distance from the deployer. And this part of operation also monitors the power state of the satellite, so it will handle any power anomalies. For example, it sometimes happens that the satellite may sit and wait for a launch for over a year, and this may deplete the battery. So in order to actually manage the antenna deployment, which takes some power, this part of the state machine will provision this functionality. And then once antennas are deployed and the satellite enters to the standard operating mode, which is it is a telecommand mode and telemetry. So there's a periodic telemetry while listening for telecommands from the ground, and also upon request it can also perform the experiment. The telemetry that is transmitted is a set of 12 beacons using 3 different modulations, and each modulation using a different encoding. And in addition, there is the real dose modulation, which transmits raw data. And this is an interesting part of the experiment because this transmission is also one of the low power transmissions that exploit the RX transmission path to transmit through that. And this serves two purposes. The first one is to attempt the communication with really low transmit power of 16 dBms, and also demonstrate that in case of a failure of the power part of the RF front end, communication is possible through an alternative transmission chain. These 12 telemetry spots are pre-configured during the initial setup, but can also be reconfigured from the ground. So we can actually telecommand and send a command to change either the sequence or the modulation schemes that these transmissions will occur. For the development phase, we are using STM32 MCUs, and we're also using the STM32 hardware abstraction layer available from ST. This mission also uses FreeRTOS, so all the management in the software happens in tasks. The hardware drivers mentioned before, we try to implement this as a Git sub-module, so this code should be reusable between projects, and actually this already happens on new projects. And then there's the testing and monitoring part of the development. For real-time monitoring, we are using the tool from ST Microelectronics, the STM32 Cube Monitor. This tool allows to, if it's visible on the right-hand side of the picture here, this tool allows to get real-time data from the MCU as the software is running, and this data can then be plotted or use gauges or text indicators to have a real-time glimpse of what is happening in the system. And this is quite useful because it actually exposes most of the actual variables that exist in the code. And so you can see very internal aspects of the software running. Another advantage of this tool is that you can actually connect to the satellite without issuing a reset or anything. So you can the satellite can keep running and during testing, and then one can connect using this tool at any time on the satellite and get the state of operation. And additionally, and this was quite useful during the deployment, the antenna deployment test, with this tool, you can actually change variable values, and that way you can also fast forward events. The most interesting thing is what we call SatNox in the loop. So this is where we actually use SatNox to test the actual satellite hardware and software. And as you can see in the diagram, we use an SDR, generated flow graph that communicates with the OSLP operator, and then also this data get fed to the SatNox DB, and they're forwarded to also SatNox dashboards. This is the flow graph, which I'm not going to explain. This is a simplified version of what it does. So it actually gets RF, it makes this a data stream, and then forwards it to a UDP port, and vice versa for the transmission part. And finally, as we can see in this nice dashboard, you get the actual data as it would have been transmitted from space once the satellite was in orbit. This has the advantage verifying an end-to-end operation, have a nice UI for your data, and have the ground segment ready for operations even before launch. Now, about the launch, some of you know, the launch was part of the Firefly initial launch that happened on the 3rd of September. And we all hoped that this would go well, but it didn't. And at some point, this was expected. So as far as we know, the payload is lost. But, well, the only thing we can do now is build more cubics. So this is what we did. We have 3 or maybe 4 new cubics already assembled. And also there was a cosmetic upgrade on the manifest that was included in these satellites. And the changes on the new cubics are we're using an updated version of the comms. No functional changes, just a bit of improvement on the PCB. We've also added a battery model in the software for better management of the battery initially during the initial conditions of the flight, and some tweaks for better software stability. These are all the people, or most of the people. I hope I have not forgotten anyone on the slide that worked on the Cubic project. So thank you all for your contributions. And this concludes this presentation, and we're open for questions.
So now you need to close your microphone, because we will give echo to the people. So there are no questions on the chat. A question for me is that how do you think that other missions can get help from the pipeline we used for testing the cubics?
Well, as we have seen in the past, many missions actually build a satellite, and then the satellite gets launched, and then everyone is running like crazy to try to receive the signal of the satellite. So using this flow, especially the SatNogs in the loop, it helps development and also makes all the missions receive ready. So it's a more relaxed time during launch to know that the ground segment already works because you used it during development.
And another question is that every year I'm saying that we should make a lesson learned presentation on OSCW, and every year we were being late and we never did that. Do you have any things as lesson learned put on from the build, the 2 times build of cubics?
Well, lessons learned. Well, I would say at first not to rush things, because once you get comfortable with some procedures, then you tend to make mistakes. And this has happened a few times. And other than that, actually, maybe you can also provide some input on that.
Okay, so if there are no other questions, we are done with this session, and we are 6 minutes earlier than the schedule. So I thank all the presenters being on time, which is something that is not usual in other conferences, but is, I think, usual in OSCW. Everyone is on time. So I want to summon all the other people from the committee, like Arthur, Red, to cheer up the people, and Doc and Keros.
Yeah.
So So are we going earlier on the break? Do you have anything to add?
Maybe, yeah. So this will be the break. Just before the break, just a message for the LLink talk. You can reach out. I mean, if you had idea like boiling from the presentations you just seen, and you want to share a quick project, you have 4 minutes. It's free. So do not hesitate to reach out to me. Give me a title, and I'll include you in the timeline for the LLink talk. All right, that's it. That's all, Mantos.
Okay. So the rooms are as following: room 1 Polaris, room 2 OSDLP, room 3 OHB LAS, room 4 LLink, and room 5 Cubic. And 6 is the lounge if you want to take a coffee with other people. So see you in a moment.
And yeah, it's this time the lunch break. The break is a bit longer, so it's like
Lunch
half an
break,
hour. Yeah, it's kind of combined with lunch break and discussion. You at 13:30.
We can learn and chat in the rooms. That's good.
Yeah, 13:30 UTC, right? Okay. See you.
See you at 1:30.
Ah, those breaks are wonderful.
Yeah,
But they're
right.
coming to an end. Just like my pizza.
Gonna stand for lightning talks. Right.
You have a standing desk.
So I have just the TV screen. I mean, that's a big one, right?
Nice setup.
Yeah.
Did you have your lunch?
Yeah. Good, good vegetables.
Very good. So next time we can kind of include this in the schedule to have a proper lunch break.
Yeah, it's hard to give the whole Earth the same lunchtime, but yeah,
That's true.
that's why I mentioned that. Where's the lunch break? But yeah, what could you put it?
Food
I have
supply.
lighting top, by the way. It's from Milenko.
Oh, very good.
That's good. I'm still. I don't know if Marcel Folaron is here. I know Michael is here. I don't have any slides from you, Michael, but you don't need any. Michael Raptakis, know you're around.
Yeah, do you listen me? Can you hear me? I have sent you some slides.
I have them. It's perfect.
Okay.
Milenko, I have, and Eleftherios Karagiannis. Is your sound okay now?
I hope so. Can you hear me?
Yeah, it's perfect.
Okay, it works then.
I got your error. We're trying to rejoin again. One of the people. I just reloaded it. It was fine, but yeah, you never know. All right, it's time. The lightning talk. So first on the line, this is you, Elef Karagiannis. I will put up the first slide. The rules are simple. You have 4 minutes. Right? You have 4 minutes. And during those 4 minutes, which are tight 4 minutes, you do whatever you want. You can stop in the middle, ask for feedback. But after those 4 minutes, we'll get the score from the audience, a yes score from the audience. So, Lev Karagiannis, Open Source Cubesat Workshop, Move 3, this is for you.
Okay, thank you very much. Thank you very much, Fred. Thank you very much also for accepting our proposal and for us being here. It's a great opportunity. So yeah, I would like to go straight away since I have only 4 minutes. So what is MOVE? So MOVE is a group of students actually. So it's the name comes from Munich Orbital Verification Experiment, where a group of students from Technical University of Munich, of course, that we run under the VAR Association. And right now we're approximately 80 students working in the project. This runs completely by students, and as you can see, we have completed the CDR, and now we have started the PDR. So we are in a really good, I would say, state. Of course, we have done something in the past as well, so we have plenty of experience. We have launched our first satellite in 2013, and then that follows up with 2018 and 2019 with the second generation of MOVE 2. Those two satellites are identical, and after that, we had the opportunity to develop further our payload, and then we had the chance to launch a balloon in June last summer, and afterwards also in October we had another opportunity to launch a second balloon. We're planning, of course, to have some more balloons in the future, and finally the satellite will be hopefully launched in 2024. As you can see, we have a normal team structure as in most of the CubeSats. So we're trying to, in the implementation, to have electrical, software, and mechanical team. And then in the design, all the different subsystems. Of course, we have the science and project management, public relations, and mission control. Yeah, what is the problem here? So the problem is the space debris, and this is what we're trying to tackle actually. So we have only 61% of satellites in space are still operating. As of 2021, more than 36,500 debris objects greater than 10 centimeters are estimated to be in orbit. And this is, of course, a threat for spacecraft, satellites, or even astronauts, because the high kinetic energy of that make even the small particles really deadly. Unfortunately, we have limited information from objects smaller than 10 centimeters because we cannot track this info from the ground. So this makes them a bit challenging, the whole topic. So here comes our project, and what we say is that we are trying to measure small space debris and meteoroid particles. We're trying to validate and enrich ESA space debris models. We try to increase the awareness of space debris, to contribute on the characterization of space environment in LEO. And finally, the most important, of course, it's at the end of the day to teach the students how to build a spacecraft. This is our sensor. So the sensor is based on the Munich dust counter, which is the box that you can see on the bottom left. And we're trying to develop some in situ measurements in LEO by making use of this sensor. We have, of course, fully redesigned the whole thing. We have redesigned all the electronic components, and we have also developed an advanced sensor that I will show you in the following slide. Here in the middle, you can see so that the MDC, the Munich dust counter, was hired in 3 other missions. So we get also the results. And also here, you can see how our 6-unit CubeSat will look like in the future. The payload, so as I said before, what we'll try to do is to retrieve flux, mass, velocity, and the crude direction of small debris and meteoroids. And we're trying to do that in impact velocities up to 30 kilometers per second. We're planning to do the calibration in the first quarter of 2022. And here you can see the 2 different sensors. We have the baseline design and the advanced sensor. So the difference so here what we did, we have 5 channels. And I can show you from here, for example, the difference that with this concept here, we can track the direction, which is something that never happened before. So this is, let's say, the comparative advantage of our mission. It's going to be some parts of the software full open source and a lot of other things also in the near future. And definitely we are open to hear your suggestions because we're looking for some new ideas on how to implement and post-process the results. But also to find a particle accelerator around Europe that we would like to test our sensor.
Nice.
On time?
Yeah.
Yeah.
Perfectly on time. That's your contact. Thank you very much, Eleftherios. Everybody, you have to turn on your microphone because you have to give a big yes to Eleftherios, or as big as you wish. And you have 3 seconds to do that in 3 seconds. Are you ready? And unmute. And 3. I want to hear you. Yes. 2, 1. Yes. It's oversaturated. See. So good luck with that. For you, there. Have a look at ESA Labs. They have this relations with the accelerators. Have a look there. And good luck. Yeah. See you soon. Okay, next in line is Marcel Folaron. Marcel, are you here? If you're not, have somebody else in line. You have 1 minute. No, I mean 3 seconds. Marcel is not here. Arthur, you're one of the new lightning talks. If you're here, you can take it.
Okay. Well.
You went on the space station all of a sudden. We don't hear you very much. No, it's very bad. It's very noisy, at least to me. Somebody can confirm?
Yeah, terrible.
It's noisy. It's noisy like that. You have a robot voice on noise. Hey. I'll take another lightning talk. Milenko, are you ready, by the way?
Yeah, I'm ready.
Perfect. So Milenko, I'll give you your presentation. So Milenko is here. Turn on your camera so we can see you. And I can see you. Perfect.
Good.
Hey, Milenko, you're fine. So Milenko, you have 4 minutes, like everybody.
All right.
You know the drill. And this is mapping open source CubeSat workshop ecosystem, some ontologies I see. So 4 minutes now.
Yeah, thank you. So this was one idea that came up a few weeks ago and is since then in my mind. The problem currently, what I see with the open source ecosystem that we have, is there are some approaches to map them, but it's never connecting. So what I would propose here is to develop a database where all of us can contribute, which links all the projects we are developing. For example, so this would be based on an ontology for those who don't know. So there's Protege, which is an open source tool where you can define basically a structure and then implement instances of that, of linked instances of, for example, software components. I've did just a very brief and simple structure here and mapped some components more or less randomly. So the idea is that, for example, if you have a certain communication interface standard, for example, the LibreCube PC104, which is under development, and you have different boards which are compatible with that, you can flag them as compatible. And if someone wants to build a Cubesat and says, hey, I want to use that LibreCube PC104 compatible board, what are the other boards which are available in the open source ecosystem? This database would basically show him, okay, you selected a comms system, for example, SatNox comms. Maybe you want to use like VST104 onboard computer with that because they are electrically compatible. Another thing would be, for example, if someone develops a telescope 1.5 unit, you could say, okay, this fits into a 2-unit structure. We have maybe somewhere in the ecosystem a 2-unit Cubesat structure available, but it wouldn't fit inside a 1-unit structure. And the idea would be that you could define your whole mission with that. For example, you start with your mission, you have a telescope, you need a structure, you need a power board, you need a communication system, and this would also amplify, in my opinion, the use of standardization in our community and would lead to faster developments of missions, because it would also, I ended here basically at the LibreSpace OSDLP, which we heard about earlier, but in the next workshop session, there will be a workshop on mission control systems, and some of the mission control systems I saw on the list there support the communication standards which are implemented by the OSDLP. So you could add another link on top of the OSDLP and give already recommendations for a mission control system. So this would make a fully open source mission architecture way more easy. And the good thing is, this is in the back end, this is just an XML file which you can open with an open source software. This could be in a repository, and we could build a website on top of that. So that's it from my side. I'm open for some feedback.
Hey, great, good, right in time. Let me turn on the camera. Hey, thank you very much, Milenko. Everybody, you know the drill. This is an amazing project and idea, Milenko. I hope you strike on it. So you have three seconds. In 3 seconds, you give your yes to Milenko. Unmute your microphone. 3, 2, 1. Big yes! Great, great. I was afraid that 3 seconds is not enough to unmute. But you're so fast, guys. So Milenko, you know what to do. Right. Next is Michael Turner. Michael, are you here?
Yes, I am. Oh,
Perfect.
oops.
Loud and clear.
Can you hear me now?
Yes. I'll make you presenter. Do you want to share your screen?
I'd like to, but I'm fiddling around with how to do it. Can you suggest something here?
Okay, I'll make you presenter. You have a new icon on the bottom.
Okay. All right. Okay.
While you're doing that, I'm checking on Arthur. Arthur, are you back?
Yeah, do I still sound like a robot?
No. Just a normal robot now.
Okay.
No, it's perfect.
I got rid of the Android.
Oh, okay. All right. And we have also, after Michael, we have another Mikhail Raptakis is here, and then we'll go with you, Okay. Okay, Michael. Did you find the icon? Did you?
Yeah, I did. I clicked on it, and the button for screen sharing is grayed out. I don't know why.
Okay. Maybe you send me your presentation so I can put it on the
Okay, let's do that. You have it,
Yeah.
I think.
I'll go with the
All
next one. Next speaker. Okay. Send it to me. Okay, Michael Raptakis. This is very flexible and dynamic. Are you here?
Yeah, I'm here.
So I have your presentation here. SatNox Tiny. So we want to hear about that. So remember the version of the SatNox client. You know the drill. You have 4 minutes. I'm waiting for your camera to come up. I'll make you presenter.
Okay. Can you see me?
Yes, perfect. Perfect.
Excellent.
4 minutes.
So,
now, let's go.
So, hello everyone. First of all, I would like to thank you for this opportunity. I am Hazir Raptakis, and today I will present you SatNox Tiny. Let's start. What is SatNox Tiny? SatNox Tiny is an implementation of a ground station satellite for a ground station for satellite observation that running ESP32 development boards using the SX1278 transceiver. Now, the main idea is to give to the user a dead simple way to set up the station, and we would like to the SatNox Tiny to be able to communicate with the SatNox network in order to perform the necessary observation. Currently, it is under active development. So, let's talk about the hardware. The main hardware that we use in order to develop the SatNox Tiny is this board that we see in the right, is the TDGO ESP32 LoRa32 board. It is a very low-cost board that has the ability to connect to the Wi-Fi, and also it came with NSX1278 transceiver. Now, the support modulation modes that this board has is the FSK, GFSK, MSK, GMSK, LoRa, and OOK. So we would like to have some observations using these particular modulation modes. Now, about the current status of the software. Right now, we have a way to initialize the board using a web application through an access point that is set up in the station. We use MQTT protocol in order to communicate with SatNox network, and we serialize our messages using protocol buffers, as it is a very nice way to serialize your message without any cost. Now, currently under implementation is the receiving and sending packets part of the board in order to proceed with some observations, and also we would like to test the implementation so far in order to understand if everything works properly. In the future, we would like to utilize an onboard screen that in order to have a more user-friendly environment. Besides that, we would like to support more boards, and after that, we go for the development. Now, some useful links for anyone that wants to involve in this project is the main repository of the project and the SatNox and SatNox Dev matrix rooms. So, if you would like to test some of our implementations, you are free to do so. Thank you for your attention.
Thanks a lot, Michalis. It's Michalis, not Michael. So sorry for earlier.
It's okay. It's the same.
All right. For Michalis, people, and his amazing project, you have 3 seconds to unmute and say a big yes. 3, 2, 1. Yes! Yeah, you heard it, Michaelis. So go for it. This is nice. Please keep us posted. All right. So Michael, we're going to try again. I've got your presentation. Maybe it's going to take time to load, but are you here, by the way? Can't hear you. Michael Eugene Turner. All right.
Okay,
Great.
so I guess I have to cue you for flipping the slides.
Yeah, or you can do it yourself. Look, it's easy. Below the image, you have arrows left and right.
Okay, tell me when to start.
Yeah. Okay. So for Michael, you want to do it like 2 minutes, 2 minutes? Yeah.
I'll see how far I get in 2 minutes, and then.
Okay. But I'll stop you at 4. So when you see me reappearing, it means it's the end, right?
Okay.
Okay. See you soon. You have 4 minutes. Do whatever you want. You can ask for feedback during the 4 minutes. It's your 4 minutes. Okay. Now I can go.
Okay, so I'm coming in from Tokyo, where it's about my bedtime. So I'll be giving a talk in my sleep. We'll see how it goes. Okay, maybe everyone knows what the KickSat mission was. Here's the actual development kit that students would use in their projects for the STEM education agenda I'm talking about. There's a little bit of history here. It started at Cornell and under an amazing professor there, but in some ways an even more amazing satellite developer. This guy did it almost single-handedly. It kind of got overhyped, but you know, at least it got launched. Failed, unfortunately. Years later, there was a KickSat 2, and that one took years to get up into space again. And but finally, there was at least a partial success. This is a 3U Cubesat, so you can, you're all Cubesat people. You can see the relative scale here. There have been some space mission proposals for these, but nothing has really happened yet at the chipsat level. I think something can happen at the STEM education level, partly because these things are so small, so cheap. I like to say intimate because, I mean, you can take a temperature reading off of it, you know, off your hand, okay? And somewhat hackable. The PC board layout is fairly simple, and there's some potential for expansion as well. And then, you know, why space? Well, space is a very different environment, as we all know, and some things like kinematics, dynamics are fairly pure, and this helps demonstrate, I think, some important concepts. Now, I talk about STEM education for the developing world. I think there are a lot of big problems there that satellites help solve, or at least monitor. And I believe a lot of these nations need their own capacity for it, or at the very least, understand what it is that the kinds of benefits that they're getting. And I think actually working with the hardware at the student level is a good approach to that. We all know that testing is a really important part of that because you can't fix stuff once it's up there. And you can also teach physical principles and technology in general that way. There's, I have a lot of various ideas for how you could make some of these testing things cheap. I'm not going to go through all of them, but you can get some general impressions here. But you know, the basic thing is that space is taught to kids kind of from a spectator level. It's like something other people do. Astronauts go up, other people launch stuff, other people build stuff. But you know, this isn't a satellite that they can work with themselves and at fairly low cost get launched themselves if KickSat 3 or something like it, what I call Mindosat 1, is made possible somehow. You should cut me off at some point, but there's a political dimension to all this, which is that even within the underrepresented developing nations, there are underrepresented areas within them. And the place I go to, it's a post-conflict zone. People there have been pushed down for centuries. And this is a way for them to be both part of a nation, but also have a lot of their own regional pride. And the students I've met there, even in the post-conflict zone with all its problems, are fantastic. Very inspiring to me. So this is one reason I go into places where there's still martial law, because that's where the opportunities for real change are. So that's pretty much my pitch. And I'd like to know what, from that really fast talk, what kinds of questions have come up for some of you? How would you like to be involved, especially at the Cubesat level? Because I have to concentrate at the education level for something this small and simple. All right, so that's...
Yeah, thank you, Michael. Thank you. If you have something to say to Michael, say it right now. You have 30 seconds. Anyone? I'm listening. Anyway, you know where is Michael? Michael, you have a slide with your contacts. Your first slide.
Join the break for discussions.
Yeah.
Okay.
Definitely. So, Michael, it's very nice. Nice you're bringing education, like for space in the Philippines. For Michael, please a yes. You have 3 seconds to unmute and say a big yes to Michael. 3, 2, 1.
Yes.
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 Of course, Michael.
Thank you.
Please stand by, Michael, and we'll have the next speaker. And during the break, reach out to everybody. Artur, are you here?
Yeah. Okay. Okay. I have this really short slides. Oh, I need to upload. You can introduce me or let me know when the time is running.
I'll do your pitch before you do it. So Artur is going to have his own lightning talk. He just thought he had something to say right now for more what is been boiling in his head from your presentations. And Artur, it's the same rule for everybody. You have 4 minutes and no more. And I bet you're going to do in 2. And if you're ready, you can go. Turn on your camera. We don't see you.
Okay, thank you, Red. So this is an idea that is always coming up during these workshops, and it's about connecting and networking. And here on the map, what you see is the SatNOX network. I guess you're very familiar with this map, and maybe some of you, hopefully a lot of you, have the stations here in the map. And how about if we don't only list, or if we would have such a application or website that does not only list ground stations, but that would list you, people, and your projects and your groups and your facilities, so that we can, make it easier to network, because we know who is where, who's working on what, and who has what, like who has a vacuum chamber, who has a vibration shaker that we could use. So I don't know how to call this thing, maybe open space community, LibreSpace community, open space network. It's up to you. I see that we have some software that is working apparently to display ground stations. So maybe this can be tailored to be used for other use cases. So to display people with the profile pic, with the skills, and also the projects that are being worked on. And yeah, I just give you the idea, but I hope somebody else can do the work. So many hands are needed, and also people to drive this if you're interested in that. So that's my short talk. Thanks.
Thanks a lot, Arthur. Thanks a lot. Yeah, apparently this is already a good idea. Like people are already like, yeah, we need that. And also like in order to connect, as you said, to network, we need to know where are people. So where are the closest one? Where's the closest facility? Great. Come on, guys. You have 3 seconds to unmute and give Arthur a big yes. 3, 2, 1.
Yes.
Who's going to work with you? That's the thing you can define in the next session of the break. Yeah? So Arthur, what's coming up next? We have a little break before going again. Oh, we have the workshops, guys. We have the workshops where you can start those discussions. We have 2 workshops planned at the moment. We have open source mission operation system and practical mission analysis with Python. Which this one is with Juan Lu, and the first one is with, let me check. Sorry.
It's me.
Yeah, that's you. Okay, so one will be the open source mission operation system with Arthur, and room two will be the practical mission analysis with Python. Maybe you want to introduce quickly what's going to happen in those workshop groups. Arthur, you can start.
Okay, I created those rooms now. So yeah, room 1 is open source mission, and the other one is the Python tutorial. And maybe okay, just to give you a quick idea, it's about there's a number of open source frameworks available for mission operations, but and maybe some of you have experience with those, and so we're going to review those, and we see what are the advantages or what is missing, and to discuss a bit about the overall framework of such a mission control system, mission operation system, what would be needed. Yeah.
Okay, nice, Arthur. And Juan, can you introduce quickly what's going to happen in your session?
Sure. So we're going to see a few concepts on mission analysis. It's not going to be a super in-depth workshop, but nonetheless, we're going to cover basic astrodynamics with polyastro, and I'm going to insist a little bit on the differences between osculating orbits, TLEs, and what it's all about. And we're going to do some visualizations as well. And if time permits, we're going to end with computing some sensor geometry and sensor coverage and things like that. It's going to be interactive.
Interactive. I feel the Jupyter notebook is not far. All right. So that's room 2 with the Juan. So you can go either room 1 or room 2. On the left, you can click on breakout rooms, and you see room 1 and room 2 listed, and join room if you wish to. And this place is going to stay up. You can stay here, and you can turn on the microphone and talk. I'll be listening, and see you soon. See you at 3 UTC back here.
Juan.
Hello.
For the bombing.
Yes, I was like the breakout room finished when I was in the middle of a sentence, so I was like kind of confused.
Yeah, we did tend to get pretty strict with time.
Yeah, as it should be.
So many participants, right? So. And I think that we should probably go ahead and start our next session if the other two sessions are finished, which they should be.
Yeah, I think everybody has kind of finished. The room closed, so.
Cool. Okay. So, welcome back, everyone. And we're going to be starting with session number 5 now. And on our first talk, I would like to invite Michael, if he's on the line. And Lefteris, if you can queue up the presentation.
Can you hear me?
Yep, loud and clear. We cannot see you though. I don't know if that was the
Yeah, I'll
intention.
turn on my webcam.
Actually, I don't have privileges to do so.
We will be fixing that momentarily. Red, can you help?
Yes, you need to upload something. Oh, oops, moved. I can take it. Michael, are you sharing your screen?
Hold on, getting on that.
You can now.
All right, I can share. Where's the share? How do I share?
You should have a button now. I can also upload your thing if you want.
What's the button?
Oh, give me a second. Do something else.
I think Michael had some videos, so it'll be better to share his screen, right?
All right.
Yep. And if they don't work, I have the backup slides as a PDF, so I can switch to that.
100%. It's coming up. So you'll have the control on your presentation, Michael. Now.
All right. Let's see. Oh, is there a way I can hold on? All right, I got the screen share.
Cool, even better then.
All right. So can you see my screen with the slide on it?
Yes, yes. Now
right,
we can
excellent.
see the screen. So, for our next talk, we have talk about the progress and developments in open source electric propulsion for nanosats and picosats at the Applied Ion Systems. And with us, we have Michael Bretty, who is the founder of the Applied Ion Systems. And Michael is an interdisciplinary engineer with an intense dedication to and passion for the fields of electric space propulsion, plasma physics, high vacuum engineering, pulsed power, and particle beam systems. So with huge experience and innovating at the edge of those technologies, specifically for their miniaturization of them. So, Michael, we're super glad to have you, and the floor is yours.
Thank you very much. And like I said, if any of the videos aren't playing, just let me know because I can't see on my end. And thank you for that introduction. So yes, my name is Michael Bretty, founder of Applied Ion Systems, and I'll be sharing progress and developments of open source electric propulsion at AIS. So as a really brief background, for those of you who haven't heard of this project or this work, currently, as far as I'm aware, AIS is really the only independent maker-based at-home R&D company developing advanced plasma ion thrusters, where I'm focusing on ultra-low cost, very easy to manufacture, and open source thrusters for CubeSats and pocket cubes, as well as providing resources for hobbyists, enthusiasts in the nanosat communities. So you can see in the picture that's actually my current setup with a vacuum chamber for testing the thrusters. It's very, very small. Actually, it's only big enough just to fit pocket cube class thrusters in. Actually, you can kind of see a little bit in the viewport. I have one of the Hall thrusters I've been developing recently in there, which I'll get to later in my slides. So first, to kick things off, at the beginning of this year, I collaborated with Care Weather Technologies to provide one of my original GPPT-3 thrusters. These were the same ones that were integrated aboard the AMSAT Spain Genesis pocket cubes. So you can see on the left, there's a picture of the Cubesat, and then on the right, the thruster sticking out of the back of the Cubesat with inside the deployer. And as of March of this year, this satellite was successfully deployed into orbit from Rocket Labs in New Zealand. So these are a couple of screenshots from the live stream that day. So as far as I'm aware, this is actually the first open source electric propulsion system to make it to orbit. And this was also my first system to make it to orbit as well. So very exciting for this effort, and kind of a big advance for I think a lot of open source initiative moving forward on such advanced technologies, now bringing it down to actually getting to orbit. So this thruster I presented on at the first open source CubeSat workshop I did back in 2019. And all the plans and everything are up and available on the AIS website, which you can check out and download. The thruster hasn't been tested yet, but it's still up there at 550 kilometers, and hopefully we'll get some results at some point. So moving forward, I've been working significantly on ionic liquid ion source electrospray thrusters. So this particular type of thruster is an electrospray ion thruster that uses a room temperature molten salt, in this case EMI BF4. Very small size, 42 by 42 by 16 millimeters. So this is a pocket cube class thruster. Right here you can see the most recent iteration, and this thruster has gone through a number of iterations over maybe the year and a half that I've been developing this system. And as of the most recent ignition test, which was a few months ago this year, the system achieved about almost 6 micronewtons of thrust at about 4,200 seconds ISP, at a little bit less than 1 watt power. So for this system, if you've been following my efforts recently, I hand modified the original Ridge emitter, which is machined into porous glass, into a single spike. So this was really the first time that I implemented a single spike emitter for testing moving forward. Here you can see a video of thruster operation in the vacuum system. So hopefully the video is playing now. But you can see the ion beam coming out of the thruster, and then there's a pause and a transition. So one of the really cool things about ionic liquid ion source is, unlike conventional ion thrusters, you don't need a neutralizer. Because of the way the fuel is composed, you can extract both positive and negative ion beams. So you can achieve charge neutralization by flipping polarities of the thruster. So you can see here the thruster is operating at several cycles between the positive and the negative ion beams as it's operating in vacuum. So unfortunately, this project has been a little bit paused because the next steps moving forward would be getting a 2D array of about 100 spikes or so manufactured for a full thruster system, which has been out of my capabilities currently. However, the system is ready to go for testing whenever I move on to that next phase. So moving forward, this year's big developments have been in advanced molecular fuels, specifically from low power micro Hall thrusters. So the fuel that I've been exploring is adamantane, which even in the electric propulsion field is pretty much unknown. It's a very unique substance. It's a solid, looks exactly like coarse table salt, that has a lot of interesting properties that are similar to iodine, which has been heavily explored in electric propulsion as an alternative fuel. So it has a high molecular weight, high ionization cross-section, a very low sublimation temperature in vacuum. So this means it can be stored as a solid, and then you heat it with low power and can sublimate directly into gas to be fed into the thruster. Unlike iodine, however, it's very safe, it's non-toxic and non-corrosive, and this allows for solid unpressurized fuel storage and fuel feed for thruster systems, eliminating pressurization and complex valving. There are key challenges, however. It's a very complex plasma and ion species that evolve. It's a hydrocarbon plasma, which runs a bit dirty. with some deposits in the thruster, and there are large beam losses and ionization inefficiencies involved with this particular fuel. So my first preliminary work has been just testing and the sublimation and ionization properties of the adamantane with a very simple discharge cell. So you can see a picture of it on the right. So I achieved sublimation at less than 3 watts, at less than 15 degrees C sublimation temperatures, very low ionization power levels of 1 to 2 watts to get a plasma. And then multiple topologies were demonstrated, everything from a basic glow discharge to ion beam extraction to neutralizer plume extraction and negative charge extraction. So here you can actually see a video of one of the topologies run to simulate a hollow cathode. So here you can actually see the plasma formation, and that's a plasma plume extraction, which is used again to simulate kind of a hollow cathode mode of operation, which would be used later for Hall thruster testing. So this again is being run on adamantane fuel. It starts as a solid and I heat it up, sublimated into the little discharge chamber, and then apply the high voltage for the discharge. So moving forward from this, I developed a micro glow discharge hollow cathode neutralizer, the GDN1. This is a very, very compact, very low power hollow cathode. So unlike traditional hollow cathodes, which require special material inserts like lanthanum hexaboride, this is made purely with stainless steel components and a 3D printed housing using Somas Perform, which is a ceramic embedded SLA, which is quite readily available and relatively low cost to get done through third-party manufacturers like Xometry. And this also runs at a very high voltage mode as opposed to normal hollow cathodes to eliminate these special inserts. So this can be run with any gas. However, specifically I developed this to run with adamantane for my micro Hall thruster developments. So you can see here actually the ultralight plume being emitted as it's being run in its self-discharge mode. So it's mounted on a Hall thruster now, but the Hall thruster is not operating. This is just testing the hollow cathode operation prior to ignition with the Hall thruster. So this was a pretty exciting development, and it was also really the first time that I was able to qualify Somas Perform for a more harsh environment of vacuum and plasma bombardment and all those things. So moving forward, this was the first Hall thruster of this development, the EHT-1 micro end Hall thruster. So it's about 1/3 of a U in size, very small fuel capacity, 3 grams. What you see here is the fuel tank, the heater, the Hall thruster head, the hollow cathode, and the drive electronics all compact together in a nice little package. The total power is about 25 watts with an expected thrust of 30 to 100 micronewtons. This one didn't have a valve involved, so it's just a direct sublimation. So it's more of a prototype system to be used for testing and developing these types of technologies. So the first preliminary test was actually run with a tungsten filament neutralizer to provide electrons, since this is much easier to get running than hollow cathode. So just heating up a tungsten filament, which ionizes the gas. So with this test, I was able to actually achieve beam, a couple hundred microamps of beam. So I did achieve successful ignition with the filament first. Then moving on, we can see here the full system test with the hollow cathode and the Hall thruster running both on adamantane fuel. So you can actually see the plume formation, and those spark discharges are actually discharges from the Faraday cup. The beam current was overwhelming my instrumentation, so it was kind of breaking down in vacuum because it couldn't bleed off the charge enough in time. But this was also, this was the first time I demonstrated a full Hall thruster ignition with adamantane with both the hollow cathode and the Hall thruster itself. I believe these first tests were also the first time reported in the field that a Hall thruster has been operated on adamantane. It's been used a few times with high power gridded ion thrusters, but I don't believe I've actually seen it run with Hall thrusters prior. So moving forward, this is the most recent developments that I've been working on. This is taking all that, all the knowledge gained from the EHT1 and shrinking it down further. So this is the EHT1 PQ pico anode layer Hall thruster. So now this takes Hall thruster technology down to pocket cube class size. So we're looking at about 1/8 of a U or 1p in size, 18 grams fuel capacity, about 10 watts of power at expected 20 to 50 micronewtons of thrust. So what you see here is everything. This is actually the Hall thruster head. There's an integrated micro valve inside the fuel tank. There's the fuel tank with sublimation heater and pressure plate to compress the adamantane fuel, and the thruster head bolts directly onto the top of the fuel tank, which the fuel just goes directly into the tank, so there's no external lines or anything like that for the system. So very, very small thruster. I believe this is probably the smallest full Hall thruster system that's ever been designed. So the electronics will sit both on the top and the bottom to bring the size out a little bit more, and I'm working on a new version that's going to be experimenting with carbon nanotube neutralizer that I haven't flushed out all the details yet, but that's also in the works. So here you can kind of see a couple of shots of the thruster. So on the left is the fuel tank, which has, again, the heater at the bottom. There's a fuel valve on one side, and then the storage inside the tank itself, and this directly bolts to the thruster head to provide gas directly into the Hall thruster. So it's a very, very compact and tightly integrated system. Again, no pressurization, so it eliminates any pressurization issues regarding launch, especially for secondary payloads, and also kind of simplifies the system as well. So here's another shot of the thruster, so you can see a little bit of the anode and the pole pieces with a prototype board on it for testing. And then on the right side, you can actually see a plume from it from one of the recent tests in a neutralizerless mode. So here is actually a video of the thruster operating in a neutralizerless mode. While this is plasma, this is not actually ignition. I did not read beam from this. So there is plasma formation, but there is not beam. So it's not quite there yet for this test. However, this was the first time I was able to achieve a stable anode layer plasma formation operating this thruster. So after this test, I switched to a neutralizer test. So again, going back to the tungsten filament neutralizer. So in this test, although you can't see the plume because the neutralizer is so bright, I was able to read much higher currents with this system. So about 2 milliamps of current, which translates with this fuel to about 30 to 40 micronewtons of thrust. So this was the first time that I successfully generated beam with the system. The tungsten filament neutralizer is not the final solution moving forward because that takes about 50 watts of power to run. So this will be replaced with the new carbon nanotube neutralizer that I'm working on. Unfortunately, I couldn't get the details finalized in time for this presentation, but that should be hopefully coming up within the next couple of weeks that I'll be sharing those details with publicly over the various AIS channels. Finally, recent development that I've been working on is a new vacuum arc thruster. It's the VAT1 PQ micro vacuum arc thruster. So again, made for pocket cube class systems, though it can be easily compatible with small CubeSats. So very low mass, very small size. The fuel is any solid metal, though typically titanium and aluminum are the most common and what I'm currently experimenting with. So about 2.4 watts of power at 1 to 10 micronewtons of thrust. So on the right, you kind of see the current iteration. It's a bit messy because it's still in the prototyping phase. However, it is moving forward. And actually, just last night, I ran this test. This was the first time that I achieved ignition with the onboard supplies because prior tests were running with external power supplies. So here you can actually see the thruster firing at a little bit less than 2 hertz. So this is actually running titanium fuel. So there's a solid titanium bar in there that's being ablated away by the trigger pulse. So moving forward, there's going to be a lot of tests coming up in the upcoming next couple of weeks to get this thing working more efficiently and getting it up to speed. And then finally, to close things out, this test was one of the earlier tests I did with much more power with the benchtop fly, so kind of pushing the system to see how far it can go. As a precaution, there is a lot of strobing and flashing, so if anyone has any issues with strobing, just look away because this can be kind of intense. So I will be starting it in a couple of seconds. So here we can see the thruster firing at much higher power levels. So this would be kind of the mode of operation if a larger power supply was wanted with a little bit more space for, let's say, a Cubesat class system. So this is running at 10 hertz, which is actually still kind of low for a vacuum arc thruster, but really pushing the system hard. Again, it also utilizes and leverages the Somos Perform housing for the bottom part that holds the titanium fuel, and then there's a special machine copper anode on the top. So that kind of wraps up all the developments that have been done recently for applied ion systems, and some of the systems have already been released under the CERN Open Hardware License V2. So you can actually download the files like the Illis one, the Pulse Plasma Thruster. Those ones have already been released, and hopefully this by the end of this year I will be releasing design files for the neutralizer and for the first end hall thruster, and then moving on hopefully once the anode layer thruster and the vacuum arc thruster are more up to speed, start getting those files out as well. So you can follow all these efforts and everything through various sources. Everything I do is completely open and pretty much done real time. So you can see the entire process from debugging to troubleshooting. I do live tests, and every test is either live tweeted and I upload video and pictures immediately as it's happening, or I do live streams and then break down the thrusters afterwards and go through every single part of the step. Every step of the entire process from the initial sketches all the way to end of life testing. So with that, I want to thank you very much for listening to this talk. And if there's any questions, the floor is open.
Thank you, Michael. With so many updates, I feel like we have to schedule OSCW twice a year to cover the progress of projects like yours. So thank you for guiding us through all the updates and super exciting things. So there's a question from me on the chat about the perceived practical applications for this range of thrust. I'm talking about the actualities of would that be used for maneuvering or any kind of orbit raising or just altitude control, right? So what are the perceived applications in terms of the impulse, also the specific impulse that you have?
Yeah. So the biggest limitation I think for electric propulsion of this, primarily the performance is limited by power. So the more power you have, the more thrust and ISP you can achieve generally. But also the size really limits the fuel capacity and also the efficiency and everything you can achieve. So when you start talking about this power and size class, what you're probably going to see mostly is use cases for primarily station keeping. So using little bursts of thrust to maintain orbit or slow your decay. You could do very small maneuvers with it, nothing huge, not kilometers or anything, but you could get a couple meters of movement here or there for collision avoidance and stuff. But primarily, I'm envisioning this stuff to be used mostly for station keeping, to keep stuff up longer, especially in low Earth orbit. The big factor again is the total impulse. Just because these systems, because they're so small, the lifetimes are very limited either on the mechanisms or the fuel capacity. the thrust actually isn't too bad. With several micronewtons of thrust or a couple tens of micronewtons of thrust, you can actually do a lot in low Earth orbit. But in order to do more with that thrust, you have to have longer lifetimes. So if you wanted to move to a system that could do much larger orbital raises and stuff, you'd have to pick a technology that would be that has inherently longer lifetimes, like FEEP, for example, which is a liquid metal ion thruster. I am starting to work on a little bit, but I haven't started fleshing out the details yet. Is something that would be suitable for this class that could be expanded to more mission capabilities. But for these systems, the small pulse thrusters, the small Hall thruster and everything, that would be kind of limited to, again, just small stuff.
Cool. Thanks. And I can see there's another question from Red about the stability of the focus and dynamic lighting adaptation for the videos, because the videos are awesome and they're super engaging also to showcase your work. And I think that Red is asking on what could be done to further the engagement aspect of them.
So yeah, those videos, I'm literally holding my phone in one hand and I'm operating the thruster in the other. So it's a bit of a janky setup. But I do definitely for engagement. When I can, I do try to do live streams. So that way people can actually interact and ask questions and things as it's happening. And when I do live tweet and everything on Twitter, I upload the videos immediately after I take them. So there is that engagement. And the phone videos are definitely better than the webcam stuff. For the live streams, the video quality is really, really bad. So I too tend to try to just upload things immediately as I'm going. But that's kind of one of the big things about this effort is these tests, every single test is done live, and even when things go horribly wrong, when they most often do, it's everyone is knowing exactly what's happening at all times.
Cool. So we are past our time for this talk, and I would like to thank Michael once again for the excellent update and answer the questions.
Thank you.
And I think that we can move on to the next one. So unfortunately, we have a cancellation for the next talk, which is the passive satellite RF tracking using the SatNox network. But I think that Red has queued up a lightning talk.
Yeah. After the whole session.
After the whole session. So we're going to be moving everything up, preferably. Okay.
If
so
that's okay.
Yeah.
We
I think
understand
that
we can
everyone's
keep
ready to do so. Yeah.
Just 1 minute. That means that if you have a lightning talk idea, this is your opportunity. We're going to insert a new session for lightning talks. So just reach out in the chat or by email, red@libro.space.
Cool. Thank you, Red. And the email is on the chat for anyone that wishes to give a spontaneous lightning talk, last minute one. We're always welcoming those. And for our next talk, I would like to invite Thanos. And hey, we can see Thanos, and can we hear him?
Hello, can you hear me? Great.
Yes, we can. Fantastic. So Thanos is here to talk about the ups and downs of developing a high-power hybrid fuel rocket. And Kronos is a mechanical engineer student at the National Technical University of Athens and the team leader of the student rocketry team of White Noise. And he is a core contributor to LibreSpace Foundation. And he's going to talk about the Kronos sounding rocket. Thanos, the floor is yours.
Great. Thank you very much for the great introduction. So, my name is Thanos. I'm the team leader of the student rocket group White Noise, and under the auspices of LibreSpace Foundation for the last 1.5 years, we have been developing Kronos. Kronos is a hybrid-powered sounding rocket, and its title is a completely SRAD and open-source sounding rocket. SRAD means student researched and developed, which means that we design, research, and actually manufacture each part of the rocket, as far as we can go, of course, in-house. So, some general specs about our kind of engine. Generally speaking, rocket engines are distinguished between three categories. First, they are the solid, which you have solid fuel and solid oxidizer mixed inside the combustion chamber. Then you have the liquids, liquid oxygen, liquid kerosene. That's some examples of liquid fuels and oxidizer. You mix them up inside the combustion chamber, then the rocket goes up. So we are in the middle of this category with the hybrid one. We have a liquid oxidizer and solid fuel inside the engine. So some general specs about our rocket. It's expected to reach an apogee of 3,106 meters, a max velocity of 0.86 Mach, a max acceleration of 10.3 Gs, and it weighs about 30 kilograms. With the propellant, of course. So the propellants are, in our case, 5.68 kilograms of nitrous oxide and 1 kilogram of paraffin. So the reason I named the talk "The Ups and Downs in Developing a Sounding Rocket." All of the 16 members of our team, of my team, actually, we are undergrads. We're engineering undergraduates, so we did not know how to design a hybrid sounding rocket. So we started with the Mark I rocket engine. You can see a cross-section of the CAD and some parts that we actually manufactured. We have to overcome major obstacles about machining. We didn't have experience machining parts, but we also wanted to make the rocket ourselves so we can have a bigger chance of learning how to do things. So we designed the Mark I. We aborted this engine because it had major issues, as it turned out, and then moved to the Mark II rocket engine. A far greater design, much more acceptable for the capabilities that we had, but also a stepping stone to learn more. So you can see on the left the PCS, as we call it, pressure control system of the engine, which connects the engine with the oxidizer tank that we actually manufactured ourselves too. And we have custom-made VAs, valve actuators as we call them, because we have two valves on board. So the time came for the first test. We needed, before doing any static tests, we need to hydrostatically test the engine and the run tank that we manufactured to 1.5 times the operating pressure in order to be sure that it will work. So we manufactured the parts. You can see the parts on the left, the inside parts of the rocket engine. We actually made them inside the hackerspace in Greece, which is the lab that we work to. And on the right picture, you can see the run tank. We also made it by ourselves, the bulkheads, everything, and the engine. So yeah, we went for the first hydro. We pressurized the tank at 82 bar of operating pressure, of the 1.5 times the operating pressure, I'm sorry. And it held great. Everything was a major success. So we were like, yeah, now we go for the engine. And yeah, the engine went boom. So you can see seared bolts on the injector head on the right picture, and the combustion chamber, like with the bolts torn, where it actually was, it had another half, but we cut it in the middle. So yeah, we went for a second iteration. That's the second iteration of the Mark II rocket engine, which actually passed 2 hydrostatic tests successfully. So everything turned out to be working great. So we have on the left side the full assembled engine. In the middle photo, we can see the injector head and the injector assembly, because we need to atomize the oxidizer before pumping it inside the engine. And at the right is one of the most complicated parts that we had to machine for the rocket engine. It's actually the graphite nozzle. It's the bell-shaped thing that we can see in every rocket engine. We had to actually make a custom tool for the lathe using a really high powerful laser in order to get the exact contour that we need inside the engine. So yeah, it was complicated. So we are really proud of it. Now that we're finished with the engine, so some words about the internal structure and the recovery system. When Kronos reaches the apogee, we need to recover it somehow. So we have 2 parachutes, a drogue parachute, which is deployed exactly at 3,000 meters, and the main chute, which is deployed at 700 meters above ground level. we've designed, manufactured, and tested successfully multiple times the recovery system with 2 CO2 cartridges. Actually, in the last test that we did, the recovery system was able to push 6 kilograms of steel, so it will totally push the parachutes outside of the rocket. You can see the assembly that we did at the left picture. And actually, with this system that we designed, we only have one energetic device deployment, the puncture of 1 CO2 cartridges, but we can deploy both the parachutes because when the time comes, the rocket understands that it has reached the 700 meters that the main parachute needs to be deployed, and actually cuts one small line, and the drogue pulls the main parachute out. So we only need to throw the drogue out with only one energetic deployment event. So about the simulations, we started using some spreadsheets to do minor calculations and stuff, but it wasn't working, of course. So Octave is the savior of the situation. We use Octave to simulate multiple things. We have a lot of calculations about the pressure buildup inside the combustion chamber. We have our own model dedicated for this, about the pressure buildup inside the run tank, everything like that. Of course, we use OpenRocket, another great open source program about simulating the trajectory. And for the CAD, we use Fusion 360 and FreeCAD for the analysis also. So a big problem about being an engineering student trying to use open source tools. We don't learn how to use them in the university. We only learn to use closed software like SolidWorks and stuff. However, that turned out to be good. Why? Because we could compare the results of free programs like FreeCAD. We could compare the results of FreeCAD that we were actually learning and didn't know if it gave good results because we were using it wrong. We could compare it with other programs close that we used and knew how to use from the university. FreeCAD tend to be great. So you can see one of the simulations that we did using FreeCAD about the structural coupler that we had. First, we were able to validate the results with software that we already knew. And then, of course, we used it for everything else. And now we do all the static structural tests using FreeCAD and also a lot of CFD processing using OpenFOAM, which is another program that we use. On the left, you can see an OpenRocket simulation and the OpenRocket model of the Kronos 2. So moving on, as far as the avionics are concerned, we design and manufacture our own PCB, which is called the Rocket Motor Controller. It's the onboard process, the onboard avionics of the rocket. They control everything. It has multiple pyro channels, multiple instrumentation and amplifier channels because we have pressure sensors all around the rocket, inside the combustion chamber, inside the run tank and stuff. It's also used to be compatible with the PQ9S format, and we actually use the PQ9S comms, the comms board used in the cubic satellites by LibreSpace. So you can see a footprint inside the middle. That's where the SatNOX comm is attached to. SatNOX comms, no, sorry, the PQ9S comms, I'm mistaken, in order to communicate with the ground station. We're now in the process of designing the 1.1 version of the Rocket Motor Controller, which is, of course, a work in progress. As you can see in the half unpopulated PCB on the top or the bottom left corner, it's gonna be a big upgrade for the rocket. However, so the control box 2, it's the classic black box with switches and LEDs that launches the rocket. We made a custom Raspberry Pi hat for the control box, and the Raspberry hat runs OpenFCT. Everything is designed in KickSat, of course. So the whole assembly of the rocket, that's Kronos. You can see the whole assembly CAD, a cross-cut version, and the OpenRocket Model 2. We actually need to test the engine somehow, so we manufactured the test stand. So the Mark II rocket engine is expected to hit a peak thrust of 4.2 kilonewtons. So we need to have a giant scale to measure this kind of thrust. So we made the test stand with 3 beefy load cells and some run tank basing and stuff. So we need, so as to be able to do the static test. Finally, each rocket needs its payload, so as not to feel alone. So we actually, some guys of the team are working for the payload. It's auto-gyro system. It has a freely spinning propeller on top and 3 fins to control its roll, pitch, and yaw motion. That's a sub-project that runs throughout the team. So where you can find us? We work at the Hackerspace GR. These are some pictures of the space. We have everything there. Everything that I've shown in the CAD and the real-life models is there. So if you're around Athens, you can, of course, visit and see every part of the rocket up close. So yeah, that was it for the rocket. I tried to fit every development update that's happened into some minutes. Thank you for hearing me, and I'm open for questions.
Excellent. Thank you, Thanos, for this presentation. Do we have any questions on the chat? And if we don't right now, while people are typing or thinking about questions, I have a question about the next steps for beyond, this version, beyond this scale of the hybrid rocket.
So, generally speaking, hybrid rockets are great for sounding rockets for this kind of category, not for bigger rockets that go into orbits and stuff. So the next step would be a bigger version of the whole thing. So a test platform, like we could call it, for even Karman line approaches and stuff. Kronos is like completely scalable for this kind of apogees. It's actually that's the good thing about the hybrid, about the hybrid engine, that you can scale it up pretty efficiently up to one point, like Rich Karman line or something similar.
Cool. Thank you. Let's see if we have any question. And if we don't, I would like to thank Thanos. Thank you, Thanos, for the talk. And we can proceed on our next talk a bit earlier, which should be Samuel. And I don't know if we have Samuel this early with us. Let's give Samuel a minute to join. Perhaps, Red, it might be
a really good time for the lightning talks, yeah. Since
while we wait for Samuel to join,
yeah. We have Jan Maas here. We need
yeah, cool, thank you.
I'm around.
Very cool. So just let me upload your thing. Voila. Yes, the talks have been advanced, so Samir might be joining in 20 minutes. That's the issue. All right, so Jan Maas reached out to me. He had lightning talk. Pretty cool topic, Jan Maas. I'm not saying anything. It's on the screen. Can you turn on your video?
Now you can also hear me. Okay, yeah, good afternoon, everyone. I just jumped through in the queue quickly. Wanted to present you something that I started a few weeks ago. It's called the LibreCube download. advance the slides. Can you make me presenter? Right. Okay. So why did I want to design something or a dummy load? Well, it's nice to have it for functional testing. So imagine you have your OBC on the lab bench. You want to communicate with something, have it as a TM source or TC sync. So to send your commands to get some telemetry from, or if you really want to push your EPS without having a payload, then also a dummy load is something interesting. And of course, I wanted to have a project. So there were some issues, so I wanted to put it on the PC104 board, but then I realized, so what do I follow now here in terms of pins? I mean, there's quite some different decisions here that we can see. And I would really take this as an opportunity to engage us to follow up on this stack connector definition. So what do I have? Well, I have a microcontroller on the board, STM32. I have two ENA 220 power ICs, measurement ICs for current, voltage, and power. I have 3 STLM75 temperature sensors, and I have 2 different I2C buses. So one connects the sensors with the microcontroller, and then one is actually for the microcontroller to talk to its onboard computer. And then we have 2 rails for 3.3 volts and 5 volts. And then we have 6 power switches or 6 power stages per voltage. And of course, I have selected now the resistance roughly that we can switch between 125 milliwatt to 4 watt. But of course, if you want to have other levels, then you just take other resistors. So this is how it looks like, well, in KickSat, but it's not only, of course, a paper exercise. So it exists in the meantime in real. And last night was the first time that I powered it up, that I flashed the microcontroller and got one of the LEDs blinking. Yeah, so that's it. It's not yet uploaded, will be soon. That's it from my side.
Thank you, Jan. Red, we cannot hear you.
Now, can you hear me? Yeah. So I was saying, as by the Lightning Talks rules, you have to give Jan Max the yes that you want, and for that you have to unmute your microphone. So please start unmuting your microphone, and at the countdown you have to give your yes to Jan Maas. Okay, unmute 3, 2, 1.
Yes!
Yes! Right, Jan Maas, keep us posted. Cube. Great. We have room for other lightning talks if you want to jump in. If you want to share something, you don't need a slide. You can do it without a slide. So please. We have one.
You do?
Yeah. Do it like that too. How can I do like slide in 1 minute? I can share an image. Okay. everyone. Keep share as I can talk about blockchain.
Because no conference is complete without it.
I don't know if I can do that. You know, it's a no-zip idea actually. Right. Okay. Let's give myself 2 minutes. All right, I'll do it. If I don't get a no, it's good. All right, everybody. So, like a few weeks ago, I proposed a OSIP. So OSIP is the Open Space Innovation Platform at ESA, and you can participate into campaigns. So you can also it's an open call for ideas, and I participated in the campaign Cognitive Cloud Computing in Space. So a lot of people presented and suggested their own AI and ML machine learning solutions. And I thought, since I'm already on a blockchain project with ESA, why not propose an ecosystem? And I've seen, being in that domain, I've seen many companies trying to jump in on this. And to be honest, I felt like it's a bit like they want to be first so that they control everything. So what we're trying to do together with the University of Strathclyde and another company in the space industry, but also anyone who wants to join, is to build a blockchain ecosystem for an autonomous consensus mechanism between satellites from different networks, from different constellations. So the idea is that we have more and more spacecraft, and sometimes they overlap in terms of activities and capabilities. And what we want to do is create this kind of ecosystem marketplace where they exchange services and exchange resources like storage or analysis and computing, or those kind of things. So this is a research study, early stage study, low TRL, and we're trying to pave the way towards blockchain ecosystem. So if you like it, and if you have a service that could join that thing, or you want to participate in setting this up, please do reach out to me. After posting that, I mean, the momentum was amazing. Got a lot of outreach. So I'm pretty sure that all the things that I've seen here at OSCW and recently in the space conferences are inspiring to me, like the IPFS Tiny, or everything that could be embedded and bring more computing. So yeah, thank you. So should I give myself the yes? You have, Pieros, you're doing it. Okay,
so as per lightning talk rules, you have to unmute yourself and give Red a yes if you like his idea. So 3, 2, 1.
Yes! Yeah, thank you guys. And of course, open source. Yeah.
I mean, you wouldn't talk about it here if it wasn't so.
Right.
I think we should start scraping and removing the open source from any title of open source Cubesat workshop, because it's a given, and it should be given, right?
Oh, sorry.
Any case. So I think we have Samuel now with us, so that we can proceed with the regular flow, almost right about time. So Samuel, are you with us?
Yep, I'm right here.
Cool, great, we can hear you, and if you can, we cannot see you yet.
Yeah, give me a minute and just unplugging my laptop from the big screen,
absolutely.
The small screen. All right.
Oh, yeah.
All right. Hello, everyone.
Cool. Yep, we can hear you and see you.
Hello, Samuel.
Thanks, Samuel.
Hello. It's been a long 1 year. What a wild ride since the last one.
Absolutely.
I hope everybody is doing well, safe, healthy. All right, Pieros, shall I begin?
I'm going to introduce you. And Samuel is a graduate student at the Stanford University Department of Aero and Astro, and a member of the technical staff at the DSO National Laboratories. He said the talk in last year's OSCW on Orbit M, which is the orbit maintenance analysis software. And this year he's joining us to talk about Cluster. I hope I'm pronouncing it correctly. A formation flying design and visualization tool on Python. He enjoys making open source astrodynamics projects in Python. And while MATLAB could be nice, he strongly believes that Python is superior to MATLAB, which is great. So thank you, Samuel, for that. And Samuel, the floor is yours to explain to us what Cluster is about.
All right. So thanks everyone for hosting me. So Cluster is a central part of a new series of projects and libraries that I'm writing in my spare time. Just because the notion of flying many spacecraft in space seems very, very difficult to the, especially in a large satellite team where you have mechanical, electrical, thermal engineers, and not everybody knows the astrodynamics very well. So a visualization tool is always needed. As a mission designer, I think we've always spent more time explaining to people how it works, why it works, and what it looks like, rather than actually doing the design work itself. So Cluster is a visualization tool for distributed space missions, and the motivation. So right now, most traditional astrodynamics softwares, STK, GMAT, and even if you do it on ORCID, you start with certain orbit elements. You have your Keplerian elements or your equinoctial Delaunay elements, and you propagate the orbits, do the Hill frame transforms, and then you say, oh, that's what my relative orbit looks like. That's what a deputy spacecraft looks like with respect to some chief. What if I don't want to do that? What if I don't want to design the orbit? What if I want to design the formation directly without designing the orbit? So this is where Cluster comes in. It gives you the power to directly input what are the formation parameters, and then it solves for you the orbital elements that give you that formation. And of course, the whole point of it is a visualization, so then it just plots out this really nice plot on Matplotlib. So next slide. So this is a lot of math, but it's basically a summary of, it's like a 2-page summary of the relative orbit elements. And what we would normally start with is our AEI, small omega, big omega, and your true anomaly. But in this case, what we're proposing is just start directly from how you want your, so this is the center of this diagram is your chief spacecraft. And this is your cross-track axis, your radial axis on the vertical, and your in-track axis here. So what kind of formations can we design if we, instead of specifying the orbit elements, I say, hey, okay, based on what the laws of physics and astrodynamics allows me to, what kind of formation, what kind of orbit will I get if I want to directly design what R subscript R is, what R subscript N is, and what R subscript big R, sorry, that's small, that's T, R, and N. So if I specify my spatial variation on the output vector, can I work backwards and solve the inverse of this matrix to get back my orbital elements? And that's really what Cluster is all about. So some humble beginnings. Let me see if Juan Louis is in the chat. Oh, I don't know if I can see him. Oh no, I was about to give him a shout out. So it started, I started prototyping a simple algorithm in PolyAstro. And in fact, if you, I think since PolyAstro version 14.0, in the contributions folder, you'll see a custom class that was written, and it's called relative orb. So if you look at the Python code on the right side, all I did was in 5 steps. So you can actually plot a relative orbit in PolyAstro in 5 steps. You call 2 orbits, one for the chief satellite and one for the deputy satellite. So that's number 1 here and number 2. And this is just using the traditional polyastro tools that Wan Lu and his team have been building over the years, which is great and fantastic, by the way. I absolutely love polyastro. And in the third step, you call this custom relative orbits class, and you just call the propagate method, and then you call the plot method, and there you go. You get the shape of the relative orbit. So this is starting with specifying the orbital elements. We haven't actually specified the formation geometry we wanted. And so now we're going to work backwards, and we're going to see whether we can do that or not. And it turns out you can, because you have 6 equations, 6 unknowns, you invert them. If you invert them, you get a closed form solution. And this eventually became cluster. So cluster, you specify the orbital elements of your chief, which is your origin, where you want what is the boss that you want your follower satellites to follow, right? And then you tell the software, oh, how far apart do you want to follow the chief? What is the amplitude in the radial direction, in-track direction, cross-track direction? And you can angle the formation planes using these 2 angular parameters here. And it just solves for you what kind of formations you can, it solves for you the deputy satellites orbital elements, which you can then plug in and use into your other astrodynamics softwares. So it's more like a visualization tool. The GUI is like a friendly starter, just to get you to understand what's actually what is visually happening when you run some of the libraries. And let's see what cluster can be used for. So at my work back in Singapore, cluster was used to design some future formation flying mission designs. So we've got 3. In literature, you'll see that there's typically 3 classes of distributed satellite systems. The one that there's the pendulum formation and leader-follower formation. So we're looking at 2 followers, and the leader is this, it's the one with the local hill frame axis. It's a bit small, I'm not sure if you can see it, but it's like teal in color. So you have one light blue follower that's just kind of following behind. So normally these are just like, they're in the same orbit, but just like spaced. There's some anomaly in between them. Then you have also pendulum formations, where you have 2 orbital planes that are just kind of like, they're crossed with some kind of, they cross each other with some angle. Could be an inclination or right angle of ascending node. And the resultant formation that you see is it just kind of moves back and forth, this is the cross-track direction as it follows the chief. So you can do fancier things. So the German Aerospace Center and designed this formation for Terasar X, Terasar and Tandem X, where they use the pure eccentricity vector separation, and it creates this nice little ellipse. Or you can get fancier, and I think the University of Toronto Spaceflight Dynamics Lab, they designed this really cool formation that kind of, when you project it onto the surface of the Earth, so you can think like it makes this funky elliptical shape that's kind of like bent, but if you project it on the Earth, it's actually it's a pure circle, right? So you can do all kinds of things that require consistent baselines, because you can prescribe a triangle or a square within a circle, and you can just make that formation geometry like really consistent. You can do things like navigation or geolocation in times of disaster and things like that. Lately, I've also been using cluster to make attitude control simple, or rather to import the use of cluster into attitude control. And these are just some plots. And because of the way cluster it solves for your deputy orbit elements in closed form, you can actually use clusters libraries to generate random formations too. So this is a bit of work in progress also. So this is a machine learning algorithm where I have a chief satellite and 8 randomly distributed deputy satellites. So I randomly generated these the relative orbits, not the orbits, the relative orbits, based on some bandwidth. I want it to stay within like maybe 2 to 5 kilometers away from the chief. And instead of trying to find what these formations are, I just solve for these formations directly, and I just iterate like 1,000 Monte Carlo trials. And it just kind of does some, and it uses some reinforcement learning to learn a policy for how do you point. So how do you point to all of the deputies in the shortest amount of time? So it's not a feature of the software, it's more of like what you can use the software to do, which is basically randomized generations of formations for your own experiments and purposes. Okay. Right, so future work. This is really exciting because I'm trying to develop a whole suite of distributed satellite missions, or rather mission software. Some future work for cluster itself. Right now it's still 2-body. I'm building a numerical propagator that includes J2 for now and drag, but I'm hoping to extend it to full order geopotentials. I might need Numba for that. And it's going to be part of a big library. I mean, maybe it might take like 1 or 2 years to finish, depending on how well I manage my time, to basically do all forms of mission analysis for advanced space missions, which is, in this case, distributed space missions are going to be the future, right? So we're going to have common classes where you can integrate cluster objects into, say, an attitude control simulation or into a machine learning library, for example. And of course, the most important thing in any project, especially open source project, documentation, right? So clusters not documented yet, have not been able, I wanted to finish it by this year, still lacking a bit. And essentially it's going to play a central role in the orchestra formation flying library. So cluster will be generating the formations. Compass, which used to be called LeoGPS. So Compass is now going to be the new relative navigation library in Python. Quadrant is the attitude control library, and control is the relative orbit control in the ROE space. And I think that's all for me. I'm not sure if hopefully I didn't run over time, and I'll be happy to take questions.
No, you're actually right on time, and that was a super interesting presentation. So thank you for that, Samuel. Let's see if we have any questions on the chat. Arthur is asking if there is a Jupyter notebook or any other tutorial that can get you started easily. I suppose that this is different from pure documentation, right? Kind of like a walkthrough.
Yeah, that's a good point. So a Jupyter notebook is definitely going to be in the works, primarily because I think that's the fastest way people learn. So yes, hopefully we can get a Jupyter notebook embedded into the documentation. I'll be finishing my final exam today, so hopefully I get some time to work on it for the rest of the year until school reopens next quarter. But yes, that's a very good suggestion. I will take that, Jupyter notebooks and tutorials. Ooh, cool. Cluster as a service.
Yep.
That's interesting. I'm not sure what an architecture for that would be like. So would it be like it's not very compute heavy. So actually in your own local terminal, you may not actually need it as a service. You could actually just download it and run it off your own computer.
Yeah. I'm
it's probably
like just before you came, I was muted. Can you hear me? Or?
Yep. Yeah.
Okay. Just before you talk, I suggested an idea on a blockchain to manage services in orbit, and thinking of maybe you have spacecraft that can run cluster because they have the computing power, but others that don't, and but they need to compute orbits or to reorganize, so they could request that as a service somehow.
Oh, that's interesting. Yeah, I actually haven't seen, like, I haven't heard of it. So right now it's Python based, but I'd love to see like a spacecraft that actually runs Python as a like as a, I don't know, Raspberry Pi with Python operations on board. That's gonna be a future. That's really fast iteration. That would be nice. Yeah.
I hope if I find time during my sleep, I'll contribute to that. That's
nice.
Keep in the loop. Ciao.
Yeah, but that's a really interesting blockchain idea, by the way.
Thanks, Samir.
And a final question would be from Arthur, whether if there are any working demos of any other parts of the library, like Compass and Quadrant and Control.
That's a good question. No, but there will be. So ideally, for every library, there's going to be full documentation, and there's also going to be walk through Jupyter Notebook where you can they tell you, oh, how do you call the formation class? How do you call an attitude control? How do you call an attitude object class? How do you call a relative orbit space object class in the control library, for example? Yeah, I think having working demos is very important, because just because if you open source your code, it's not yet fully open source, because it's very difficult for people to read and understand until you actually have a working demo and at least you explain what's going on in the code, right? So yes, I totally agree. I will have working demos for it. Hopefully, the first version will be out by sometime early next year to end of this year. Yeah, that's a great idea.
Cool. All right. So if there are no other questions on the chat for Samuel, I think that we can thank Samuel once again for your talk. Thank you. That was super interesting.
Thank you.
And with that, I think that we are concluding this session. That was session number 5, and we're gonna take a slightly longer break this time, from now until 4:40 UTC, so 16:40. When we're going to be convening back here for session number 6 and a few more talks until the end of this year's open source Cubesat workshop. So see you all in a bit. There's going to be, as always, break rooms. So room number 1 on electric propulsion, room number 2 for Kronos sounding rocket, room number 3 for cluster. If you want to join the people that are behind these projects and have a longer chat around it. And as always, there's always room number 4, which is lounge, just to chill and discuss for other topics. So see you around at 16:40 UTC for session number 6. Thank you all.
Everyone, a little information. In order to join the breakout rooms, you can click on the left, breakout rooms, and choose room 1, 2, or 3 according to the different presentations that were given, or join the lounge on room number 4. See you there. Next session is at 16:40 UTC.
Hi. Good. Welcome back from the break. Okay. So tells me that my connection is not really good at the moment, but I would like to know if someone can hear me.
We can hear you.
Good.
Hello, Artur. We can hear you.
Okay, very good. Then it's time to start the last session of this year's workshop. And it's going to be a super interesting and fully packed session. I'm very much looking forward to it. I'm hosting it together with Red. And
yes,
Red is here as well.
yes.
Very good. Good. Okay. So our first speaker in line is Michelle Thompson. And it's really giving me a hard time because I have no idea how to introduce her, because whatever I will say, it's not gonna do justice to her. So I think the best is I'm going to use her own words for that. And I also have to mention, however, that her internet connection is not very stable in the moment. So likely we're going to watch this as a video, unless Michelle, you are here and you would like to try, give it a try.
She muted.
Oh, hi there. Hi, I'm here, but I only have audio.
Okay, but you can see the presentation, so you could talk along the presentation, right?
It might be a good idea to play the video if you can.
Okay, there we go with the video. So Michelle, in her own words, she enjoys thinking and doing, not necessarily in that order. And she has a master in electrical engineering, in information theory. She has worked in landline and satellite telephony, serves in a variety of volunteer positions in the amateur radio community. And she is co-founder and current CEO of the Open Research Institute. So what is the ORI? It's a research and development organization that is a non-profit. She's one of the previous board of directors was Bruce Perrins, and Michelle and Bruce, they both attended the workshop in person.
Hello, everybody.
In Spain. So that was a very exciting time. And so the ORI, so one of the main important purposes of it is to facilitate the worldwide collaboration and the development of technology that would otherwise be restricted under national laws like ITAR and EAR. And also they are on the forefront of fighting for open source, and we have to be very thankful to them for that, because they really basically started this movement on a terrestrial layer, I would say, and we can now apply this to space, and still Open Research Institute is going to support us in that, and how that we will hear now from the talk. So what I'm going to do is I'm going to play you the video, and later on we are going to address some of the questions to Michelle. She is available in the chat, and her audio is also working.
The video was on, Arthur.
The video was on already. Okay, sorry.
Hello, everybody.
All right. Okay. So,
I'm Michelle
okay.
Thompson, W5NYV, and I'm here to tell you all about.
Okay. Is it playing? All right.
Okay, it's not playing for me. I try it again. It's my first time. So 3, 2, 1, go.
Not playing here, Otto.
Okay, let's do the following because I follow the instruction
Hello,
of
everybody.
big blue
I'm
button.
Michelle Thompson, W5NYV, and I'm here to tell you all about what Open Research Institute is
No?
and what we have been doing. Open Research Institute, ORI, is a nonprofit research and development organization which provides all of its work to the general public under the principles of open source and open access to research. As we all know, these mean particular things, and those things have to be defined and they have to be defended. Open source is a type of intellectual property management where everything you need to recreate or modify a design is freely available. As a baseline, we use GPL version 3.0 for software and the CERN Open Hardware License version 2.0 for hardware. All we do is open source work, primarily for amateur radio, space, and terrestrial, but also some other fields, as you will see. So who are we? Here's our current board and our immediate past CEO, Bruce Perrins. We have one opening on the board, as Ben Hilburn, one of our founders, very recently retired from being an active director at ORI. He remains as one of our senior advisors. We are looking for someone to join ORI board that supports what we do and wants to help make it happen. It's an active role in a flat management structure. Board members are experienced in management, engineering, operations, and technology, and 3 out of the current number of 4 are from underrepresented groups in STEM. As a board, it is our mission to serve our participants, developers, and community members. We now have at least 535 people that participate in what we call the open source triad, our mailing list, our Slack, and GitHub. All work is organized in independent projects or initiatives. We have some affiliations, and we proudly ascribe to the Open Space Manifesto from Libre Space Foundation. We work with radio organizations, several universities, and have worked with a variety of for-profits. What do we do? Here's a visual summary of top-level projects and initiatives. The vertical axis is risk. Higher risk projects are at the top, and lower risk projects are at the bottom. Maturity increases left to right. Maturity may indicate schedule, but the score is also influenced by complexity or difficulty. The color of the shape indicates how much stress that project is under or what the risk level is at this time. The size of the shape is the budget estimate. By far, the largest budget, riskiest, and least mature work is in the aquaphage project, which is an open-source bacteriophage research and development. Bacteriophage are viruses that attack and destroy bacteria. This is a biomedical project and not amateur radio. This project has been halted by COVID and has not yet resumed. Our digital multiplexing payload project is called P4DX, and it's in the middle in green. This is a multiple access microwave digital regenerating repeater for space and terrestrial development. Channels divided in frequency are the uplink. The uplink is on 5 gigahertz. The processor on the payload digitizes and multiplexes these signals and uses DVB-S2X as the single time division downlink. The downlink is on 10 gigahertz. The system adapts to channel conditions and handles things like quality of service decisions. For example, low and high latency digital content. The uplink is divided up using a polyphase channelizer based on the open source work done by Theseus cores. For the current prototype, we are only using MPEG transport stream, but generic data is the goal with GSE. The prototype beacon signal is 5 MHz wide, and we are using 1 modulation and 1 error coding at this time. We're not yet rotating through all of the allowed combinations in DVB-S2 and S2X yet. Our prototype work can also serve as a terrestrial multimedia beacon. Work was demonstrated to groups with mountaintop spaces in October 2021, and deployment will be as soon as possible. M17 project is an open source VHF-UHF radio protocol. Think open source digital mode HTs and repeaters. This project is only slightly more stressed than P4DX, but it's further along in maturity because it's narrower in scope. We believe M17 project will be very successful from current development to scaling up to commercial product launch. The M17 protocol is the native digital uplink protocol with some modifications for microwave for P4DX. We are working hard to get M17 on and through more satellites and on more sounding rocket tests today. Engineers General is our initiative to hire highly competent open source workers to reduce burnout and increase quality in open source work important to amateur radio. We have 1 contractor currently, 8 resumes, and have applied for funding for 2 more. We are actively looking for funding for the remaining 5. The Bird Bath is a large dish antenna at the Huntsville Space and Rocket Center. This was used in the past, but has been parked for decades. It took 2 years of negotiation, but ORI has the support of the museum and permission to begin work renovating this dish for citizen science and amateur radio educational use. Work parties from earlier this year were rescheduled due to COVID. Upper right, there are 2 completed projects. One is ITAR EAR regulatory work. It took over a year, but we received a determination from the State Department that open source satellite work is free of ITAR. From U.S. Commerce that it is free of EAR, and we obtained an advisory opinion that publishing on the internet counts as publishing under the regulations. This is a huge step forward for not just amateur radio, but anyone that wants to contribute to open source space work. Debris mitigation regulatory work took 10 months to complete. The process culminated in a highly successful meeting with the FCC Wireless Telecommunications Board, the Office of Engineering Technology, and the Satellite Bureau in late October 2021. Lower right is battery matching, a project that matches NiCad cells for very durable batteries in the style that used to be done in amateur satellites, and puts the methods and documentation in the public domain. Ambisat-inspired sensors used to be on the bottom right, but now it's bumped back a bit in maturity level and is a bit higher risk. This project was supposed to be a project done by students at Vanderbilt University, but no students materialized, primarily due to COVID. We had 1 kick-butt professional volunteer who was working on a 10 gigahertz beacon that would go onto the sensor connector on the main board. But the project was moving slowly overall, and ORI decided to provide additional operational support. Additional volunteers joined the team, we reviewed the finances, and then took some actions. We updated the main Ambisat board to move it from the ISM band it was in to the 70 centimeter ham band. We improved power and ground and addressed some other design concerns. The boards are back as of last week, and software and firmware development is underway. The 10 gigahertz sensor beacon work is proceeding quickly as well. Ambisat is an excellent educational platform, but the ISM band decision wasn't the only problem with it. It's a very small board. We decided to look at combining the 70 centimeter Ambisat with another open source satellite board to make a combined spacecraft design. I reached out to Pieros Papadayas at LibreSpace, and we are moving forward with using the SatNog's comms project. We look forward to contributing to the FPGA codebase and flying both Ambisat and SatNog's comms designs as early and as often as possible, starting with sounding rockets and ending up in space. All of these projects are open source, and all work is published as it's created. When? Well, we have timelines. We were incorporated in February of 2018, got our 501c3 in March of 2019. We hit the ground running and haven't stopped since. We'll distribute a copy of the slides so you can see our wins and losses along the way. There's a lot going on here. Here's what's been going on since March and the future plans that we know about. We use Agile framework for management, and most of us have some sort of formal certification, either completed or in process. This is the Agile Manifesto, and it is the foundation of how our board decides things and how it supports project leads and volunteers. Note the second item, and put in the word hardware instead of software, and that's one of the reasons we demonstrate early and often and incorporate the feedback quickly. Where are we? Here's the locations of the concentrations of current major contributors and participants. When we say international, we mean it. Our participants have a wide range of ages, are generally educated in engineering, come from a variety of backgrounds, but they do tend to be relatively young and male. We have some physical locations that are important for carrying out the work we do. Remote labs are lab benches connected to the internet that allow direct access to advanced lab equipment and 2 different large Xilinx development boards and DVB S2 and S2X gear. We have relocated our second remote lab equipment from US Florida to US Arkansas and have added a 3-dish interferometry site for amateur radio and public science use. Remote labs are here for you all to use. If you need or want large FPGA resources and test equipment up to 6 gigahertz, then we have your back. We bought Open Lunar Foundation's satellite lab. It's in storage, waiting for the M17 Project Lab construction to conclude, and then the equipment will go there to pack that lab full of wonderful test equipment, materials, and supplies. Why do this? We believe that an open source approach to things like amateur digital communications, bacteriophage research, and sticking up for the non-commercial use of space will result in the best possible outcomes for the good of humanity. We have a lightweight, agile approach to doing things. We keep our overhead very low. We are radically participant-focused, and the work must be internationally accessible. You can see that public demonstrations and regulatory work are given a high priority. Working code and working hardware are highly valued, and working means working over the air. Thank you to everyone at LibreSpace for the support and opportunity to present here today.
All right, thank you very much, Michelle. Thanks for preparing that for us. If you're here,
yes, Michelle, thanks very much.
Oh, you're very welcome. Thank you so much for the opportunity.
Red, can you change the slide because we can just go to the
I will do it if you want.
Okay, I do it. So at least we see the background. Okay. Wow, that was amazing and very inspiring, and it's totally in line. I think what is the goal of this workshop, and for me particularly, I was when I saw Light White. I mean, I'm totally in. Yeah, keep things simple, accessible, understandable. But let's see. Do we have questions from the chat, from the audience? I see Jan Peter is typing. We see the questions coming in. Meanwhile, so you mentioned a bit the process of how to join the research institute. Maybe you, Michelle, you want to go a bit into detail there?
Sure. No, I'd be happy to. So we don't sell memberships. We're not a membership society or amateur radio club. And I know that does disappoint some people, but we did this on purpose in order to not compete with membership societies. But joining means if you join, you're welcome. As a participant, we do ask that if you join Open Research Institute as a participant, you're usually joining through a project because we're project based, and then we ask people to commit to a code of conduct, and that's a very standard code of conduct, very similar to the one at LibreSpace. And that's it. That's it. As long as you are willing to commit to that, then you're welcome, and you are in ORI. From a project perspective, we have a short guide on our website at openresearch.institute. So if you have a project that you would like some help with, that you need a 501c3 in the US to help sponsor your project or to support you, then we have a guide for that too. So there's 2 ways to join. One is a participant on a project, and one if you have a project that needs a little bit of help, a corporate structure that's aligned with your goals.
Okay, very good. Jan Peter is already interested in making a podcast about it, so I think he will contact you in the next days. And Red is asking, do you have example of support made by the Research Institute to non-US projects? Is that possible even?
Yes, it's possible. We've done our homework with respect to the United States Internal Revenue Service, and we do have to fill out extra paperwork, but we've already supported people in Italy, Poland, the UK, Germany, and I think that all we've given is advice to Japan, to people in Japan. The thing that matters is if you give any material support. But yes, we are prepared to give full support internationally. And I should put an asterisk there. You know, we do our absolute very best to make sure we comply. If we do run into any sort of issues with limitations that we have, then we'll raise them with that particular group or individual along the way. But no, there isn't any impediment for sharing information or data. We pursued a regulatory path of protecting our volunteers and putting that first and foremost. So there isn't any danger in doing open source work internationally. And our goal is to also provide material support for anybody around the world.
Okay, thanks very much. Unfortunately, the time is progressing very fast, and I think we have to conclude here, but I'm sure there will be more questions in the chat. You're available in the chat for the next for the time, right? And
Yes,
actually,
yes,
you're always in the chat available.
Yes.
So looking forward to that. And so thanks. We're going over to the next presentation. So the speaker is Glenn, and Glenn really prefers to keep a fog of mystery around him, around his person, because he didn't share his biography with me, so I can't really tell you much about Glenn, but I can tell you a bit about his talk, and it's, as you can see, it's about the communication protocols for both, so for the communication system on board Orsat, but also the ground station part. So we have both space segment and the ground segment part. Meanwhile, Glenn, are you able to
Yes,
use your microphone and your also your camera?
Okay.
Great.
I'm trying to figure this out. Okay. I sincerely apologize. I did send the bio, but maybe something
No problem.
how I sent it. I can just quickly say I'm
okay, hand over to you, yeah, Glenn. I leave the stage to you.
Am I on?
Yeah, you have 12 minutes, and then we have like 8 minutes for questions.
Right.
Thanks.
So I'm communications team lead for Orsat. This sort of follows the 4 presentations or talks yesterday. Essentially, what I'm talking about here is from the data link layer and below, so mostly the hardware. Orsat is a project that originally started with Orsat 1 with the Cubesat launch initiative. And we came to the realization that we needed to get some flight heritage first. So we came up with Orsat 0 and then subsequently Orsat 0.5 to test out some of the things before we go into the real Orsat 1 flight. What Orsat 0 is primarily going to be doing is testing out communication channels and the power system and the battery and essentially the bus. And so of sincere or significant importance is communication channels. So on the left, we have how we're going to be presenting to the amateur radio community. We are using amateur licensing for Orsat, so we need to give something to the world, and we're intending to use SatNogs to schedule observations to pick up our APRS beacon, which contains our engineering data. We were initially going to be putting on a CW component as well, but that's not on Orsat 0. It'll probably follow subsequently. And then on the right side is our actual engineering data link. And we're basically providing a L-band receiver that is receiving all the time. It's dedicated to receiving. And so what that means is we actually have 2 transceivers or 2 transceiver chips on the spacecraft, and one of them is dedicated to receiving on the L-band at all times, and the other one is primarily transmitting the beacon or the downlink acknowledgement or responses to the uplink, but it could also be switched as a receiver as well, so there's a little bit of redundancy there. So we go up on L, and the reason for that is because we wanted to put into place an underutilized band. L is an uplink only in the space segment, and we don't have bandwidth or bitrate restrictions. We have a bandwidth restriction, but no bitrate restrictions on the actual channel. So we're moving as fast as the transceiver chip will allow at 120 kilobits per second. On the downlink, we are restricted by the IARU and the ITU regulations on 70 centimeter in the space segment. And being an unspecified protocol, which is a very odd thing to say, we're able to push up to as fast as 100 kilohertz of spectrum, or we chose 96 kilobits per second as our downlink. These are the emission designators and the details of the emissions, what we are expecting for our signal to noise ratio, or EBNO. Basically, we're going to complete our link budget. I didn't include the link budget details here just because there's not enough time. But the important thing to realize is that over here in our UHF beacon, we are using the G3RUH APRS packet over X25 data link, so that we can be picked up by nearly everybody in the world. And it's only when we go to the EDL links down here do we go into the non-standard bit rates. So the transceivers. I realized that I forgot to include a slide here. However, it's probably not the only thing I forgot. This is the block diagram of Orsat, and then the highlighted sections are Orsat 0. So the highlighted sections are just the critical subsystems. And my focus is primarily on the antenna and on the C3 board, the command, communications, and control. And then here you can see the AX5043. There's two of them. One of them is dedicated for downlink on the L band, and then the other is actually up and down. So there's a low noise amplifier and a power amplifier. So we can put that into either mode. This is the block diagram of the LNA. Of interest is that the AX5043 can only go up to about 1 gigahertz, and so to pick up the L band signal at 1.2 gigahertz, we had to put in a down converter, and so there's a lot of extra hardware here. However, it's been proven to be pretty reliable. We're using a synthesizer from Silicon Labs to do the local oscillator and a mini circuits mixer. The transmitter basically has the second AX5043, a power amplifier that can put out plus 30 dBm, directional coupler so that we can measure forward and reflected power, and then the low noise amplifier for the receive channel, and it's all basically driven by this switch right here to switch the modes. The antennas are basically ordinary tape measure arrays. We're using a quadrature fed canted turnstile, and we're using mini circuits hybrid directional couplers to feed those 4 elements in quadrature. Earlier in the mechanical presentation done by Marvin and Hayden, they talked about the cards having a insulated connection to the anodized frame. Well, this is an example of one of the cards that actually require an electrical connection because the actual space frame is part of the antenna system. Similarly, and that was the slide that I was hoping to, I forgot to do, was the C3 board actually has a physical electrical connection to this space frame so that we can dissipate heat from the power amplifier. In terms of the beacon, we're basically sending the ordinary things that one would expect for spacecraft health, and in particular for the radio stuff, we're sending down the received signal indicator, phase lock loop status, temperature of the PA, forward and reflected power, and other RF related things, in addition to many other pieces of data that's relevant to the spacecraft. This is obviously published. IRU has the links to our pub directory that contains the details of our beacon format. And what was I going to say? Yeah, so there. How do we transition between beaconing and the engineering data link? Okay, so this is how we start up. When we get pushed out the back of the deployer, whether it be a P-pod or the ISS, we start a timer that goes at some period of time, particularly 45 minutes for our current launch. And we go through the steps of determining if we have power, if the temperatures are okay, if everything has actually been deployed, the antennas in particular. And then we drop down into this state machine here in this loop where we basically go back and forth between listening on the EDL, the L-band uplink for a transition to the EDL mode, or do we just sit there and beacon? If the power's good and we haven't been told to go into EDL mode, we'll just sit there and beacon. And that allows us to be picked up by the amateur community. That is pretty much all the pieces on the spacecraft. Now, in terms of unit clogs, this is our ground station system. Quick block diagram of the things were based on the Lime SDR transceiver, and we have basically all the front end equipment there. We're talking with circular polarized Yagi antennas and quad helix antenna, power amplifiers, monolithic amplifiers, and then antenna mounted LNAs. Down on the power and control, we are basically running a power board that turns on and off all the components from the above part, plus operating the controller. This is our power board that operates all the little components. That's the actual station. The UHF is on the left. We actually include a VHF antenna as well, so that the station can be used for other purposes. The quad helix antennas for the uplink. And this is all on top of the roof of our engineering building. And down here in the bottom is the enclosure that contains all the components that were on that previous sheet, which basically is all squeezed into this box right here. It's pretty tight. The station is controlled by the, there's two Rock 64s, one that's running GNU radio for the SDR, the other is for running a state machine that we call a state daemon, or a station control daemon, and this is the state machine that's running station control. And then the GNU radio flow graph, half of this, well, the flow graph is all entirely running headless on the second Rock 64 on the ground station. And basically from the Lime SDR to UDP sockets. This is the receive side where we can simultaneously receive both the beacon and the EDL. And then this is the transmit side where we're basically transmitting on the L band, and we have the ability to re-enable this section up here to transmit on UHF if we're having trouble with receiving on L band. And this is what it basically looks like on a workstation. So the idea is that the entire station is remote mountable. It can be put anywhere. We're actually building two more. We've got one just about completed at a second location in Portland, and then we have one actually being built at the University College of London, with future intent to possibly build one in Hawaii. So once these stations are deployed, basically all you are doing is you're remote accessing into it. And on the workstation side, you would either be you would be running gpredict, even though that would be running on the station enclosure itself, but that's where your mission control stuff such as late yams and the other side of the GNU radio head where you can actually render the SDR data. I think I have covered everything. Future plans is to get that CW beacon back onto the downlink. We have intent to go to DVB-S2 for mission stuff. Again, what I said was this was the primary critical subsystems that I described, essentially what we refer to as the bus. In terms of mission stuff, we would possibly be doing either DVB-S2 on the S-band or X-band, and we're also doing a DX Wi-Fi experiment on S-band. We would like to integrate into SatNogs in a way that we can actually deploy the transmitting capabilities, although we're unsure on how we would proceed with that. And we would be open to receiving QSL cards for those people who receive our beacon. The call sign, which we have, which I have it on my last slide here, is open or is available on QRZ, so people can find our information there. Orsat 0 is launching on January 10th of this coming year, or no sooner than January 10th, I apologize. And that is a picture of Orsat in its fully stowed mode, ready to be deployed. And there are the links to things that point back to us. And I think I did it in the right amount of time.
Glenn, thanks very much. That was also excellent timing. And you managed to compress a lot of information into this 12 minutes. I think it will consume all my holidays now to go through the GNU flow charts. But amazing. So let's look in the chat. We have Pieros. He is mentioning that you should not forget to submit the beacon format to SatNox.
We will
so
do
that
that.
you
Absolutely.
can
Yes.
decoding.
We will have that done in the next week or so because time is ticking for us. Yes.
Right.
Thank you
The
for
launch is upcoming, right?
Yep. The beacon is actually on our pub site, and we handed it to the IARU, so we'll give you the link to that. And we've got Dmitry McGluckin, who's been working with some of the people at Libre Space. So we'll make sure we get that there.
Okay. Patrick says hello. And then there's Risto. Yeah, our next talker, he is asking if there's a QSL card design.
We're working on it. It's going to be some part of our Orsat logo, and yeah, we're going to put that together. That's going to happen before we're launched. In fact, I think Risto's going to be the one that gets to do that.
Very good. Red is asking if there's full telemetry decoder for Polaris. Not sure if this, maybe there's some.
I'm not sure.
I'm asking. Sorry, Glenn. Now this is Red. I'm asking because I'm not sure. I know what beacon decoder is. If it's used to and decode all the telemetry that you have on Orsat. The reason I ask is because Polaris is a machine learning project that learns from the telemetry, and we could run it if you have this as a potential.
Okay, yeah. That's good to know. I just did a screenshot, so I'll have your message there on a screenshot. Let's see. We would like to know the best approach to getting our beacon format published so that people can decode it. And it should be on our website, orsat.org. And I'll reach out to whoever your best advice to be is to do that. Yeah.
Thanks a lot. Yeah.
Okay.
Do we have more question in the chat? Don't see one. I have one for the ground station, so it's mounted on the roof. Mm-hmm. Is it? How about the maintenance? Is it possible to flip it down? I didn't see that.
Well, it's not very high, so we take a small step ladder to reach it, and we could also tip it down so it's pointed to the horizon. The park position is where it points to zenith, and so that brings the feed points and the LNAs and all that down to the ground pretty low. I mean, if you were to go back to that picture, you would see that that it's kind of belly button high off the ground. I mean, if I this point right about here is about where my belly would be. So I could actually reach up to this. However, that being said, on some of the other sites, we have this separated by some greater distances. And so we are running some pretty good coax. We're running heliax off of this thing. So we can separate these by about 30 meters from the actual antenna structure. Here we're less than like 10 meters or 5 meters. Yeah, the maintenance on that is not too bad. The big challenge for us was actually getting permission and access to be on the engineering building roof. It was the funniest thing. You see these yellow kind of railings around us. Those were specifically put so that we don't fall off the roof, which we would never do in the first place. But anyway, yeah, it's kind of funny.
Well, maybe if you do the celebration of the launch and you with the beer up there, huh?
That would.
Who knows? So I think that's the rule there.
Right.
For the
Yeah,
students,
absolutely.
huh?
Right.
Good. Okay.
Okay.
Thanks, Glenn. So we're
Thank
handing
you
over
for
from.
the opportunity.
Thank you.
Bye.
Yeah, we're handing over from one Orsat presentation to the next. So next in line is Risto. And yeah, almost 1/3 of our presentations were around Orsat, which is very good. So it shows that, well, there's a lot of information, and we are very glad that you're sharing this all open source with us. And we're going to see then in the future the offspring of the seeds that you're digging now. And so the next talk is given by Risto. He's a master student at of systems engineering at Portland State University, and he is in the Orsat project since 2017. So he also works, and this is maybe a kind of a not it's a not a well-known secret now. It's that you're in a space company that is using Orsat to design a commercial space mission. But maybe I should have not said it now because it's still a secret, or maybe it's not a secret anymore. You let us know. So the talk is about using doing mission planning for Orsat and using Eclipse Papyrus SysML. Eclipse is this framework, Eclipse rich Java-based framework, but it provides you the tool to do SysML diagrams. And I've invested myself time in this as well, and so I'm very interested to hear about your experience and to see your slides and to hear your talk. So the stage is yours. Please go ahead.
Right. Thank you, Archie, and everybody here. Can everybody hear?
Yes, yes. All right. Yeah.
Okay.
Yes.
All right. Hello, everybody. I am Risto Rushford, and I'm getting feedback from myself. I'm getting this here. Okay. I'll attempt to just talk over myself for now. So I'm a master at Portland State University, and I've been working on this project just for the past quarter, so it's not as well developed as it really could be, but it's something that I'll be working on for the next several months. And thank you. I'm not sure how to put.
Do you have a headphone that you could use?
Are you hearing? Were you hearing me double as well?
No, no,
Yeah,
we hear you
did.
fine.
We hear you fine, but we hear a little bit of noise at the back.
Now I'm cutting out. Interesting.
Just keep talking and go on. I think it's okay.
I just muted my computer, but you should still be able to hear me through the mic. Is this better?
Yeah, it's much better. Yeah, there's not the noise.
Okay, let's just go with this for now. It was hard to talk over myself. So I'm gonna go through this really quickly. You've probably seen plenty about PSAS, but it's in the slides in case these get shared and people want to see it. We're an extracurricular, interdisciplinary group really focused on hands-on student projects. I've been very involved in the interdisciplinary part. My focus on the Orsat project since 2017 has mostly been in the realm of project management and administration. And then once I got into grad school in fall 2019, I started learning about systems engineering. And I'm excited that this will be my first semi-publication in the area of systems engineering on the Orsat project. You've probably seen this picture already. We're a group that does amateur rockets, and the flight computer of our rocket became increasingly sophisticated. And at some point, we realized it wasn't all that different from a Cubesat. And then where I came in was actually right after this proposal was submitted, so I won't take any credit for that, but I did come in just before we got the acceptance letter from NASA CSLI, and I've been involved ever since. So the importance of mission planning, to put a little bit of foundation on this presentation, part of what has motivated me to start working on this is lessons learned through the Orsat project, things that troubles that we've encountered along the way that we're like, okay, that might have been something we should have considered, or we did think about it, but we didn't really plan well around it. And so that was part of what got me interested in systems engineering and this model-based systems engineering project. So yeah, for mission planning, I'm sure you all know this, space is hard, and you can't think of everything, at least not right off the bat. So having a model that you can work with as you go is very useful. It's hard to plan for. There are a lot of requirements. This is just a subset of all of the requirements that you have to plan for. This is an example of a requirements diagram, by the way. There's a lot of context. You've got your mission enterprise, you've got your spacecraft and various other organizations and entities. You've got your space environment and all these things affecting your mission that you have to plan around and interface with. There are complex scenarios that you have to be prepared for. This is a use case diagram for the Orsat Live mission, which I'm very excited about when we finally get that up into space. And so it really helps if you can track and trace all of it. And so that's really what this what I'm working on is a tutorial to use this Eclipse Papyrus tool, which this is a screenshot of, to help make it easier to build models that can facilitate growing the project from your initial concept as it grows in complexity, and to manage and trace the requirements along the way. SysML stands for Systems Modeling Language. It's an extension of UML. So if anybody here is familiar with that, it's very similar. It has some modifications from the UML2 specification, plus some additional diagram types. The thing about it is like everything is specified so that anybody who's familiar with the specifications can look at any diagram and understand what's going on, hence the language part of it. And so that's to give everybody working with the model a common basis for analysis and design. And then Eclipse Papyrus, as Artur mentioned earlier, it's an open source project to provide an integrated environment for editing UML and SysML models. It's built on the Eclipse platform, and it I've found it to be very useful, but not always intuitive to use. Inspirations for this are also space mission engineering. I've been using this very heavily with my work to develop my workflow. And then SysML Distilled and architecting spacecraft with SysML are great resources on using SysML, but they don't really, they show you what the end product should look like, and they explain the pieces, but they don't really tell you how to put it together. And that was the point for this slide. And hence this tutorial. I will say it's very much a work in progress right now. I only have a couple of sections that are currently up, but they are available on GitHub. If you go to the Orsat GitHub page, it's under Orsat Mission Planning. And I have these two sections. This one tells you a little bit about SysML and how to install Eclipse Papyrus. And this one tells you how to start a project. And the next one that I have up will be about doing the stakeholder analysis, hopefully in the next week or so. And so, yeah, if anybody wants more information, check out the Orsat website. You've got the full Orsat resource at github.com/Orsat. You can contact the PSAS group at aerospace@pdx.edu or contact me directly at risto.rushford@gmail.com. And let me turn my sound back on, sorry.
Awesome.
Okay, Risto, that was very good and very fast also. So we have plenty of time for questions. So the audience can either write a question in the chat or just shout out. Andrew is typing. Can you talk about how to get started on Papyrus? Yeah, and I actually also have a follow-on question on that. Maybe Papyrus and Topcased. But let's first go with the how to get started with Papyrus.
Sure. Am I able to do this?
You can do screen sharing.
Yeah,
if you want to open the
link. You want
link.
to do screen sharing if you want to do that. At the moment, you see the presentation from the conference.
So you're in presenter mode, and on the bottom, there's these 4 buttons, and the very right one, exactly, you found it.
Okay, so I think I can just type in this. I can spell. So you can go to .org/Papyrus and the download page. It's actually very easy to download. Setting it up is difficult. So whatever system you have,
it's the second one.
Download as a zip file.
Mm-hmm.
And let's finish it. Looks like that's going to be complete. Just unzip it into your directory you want to work from, and go into there and click the Eclipse button or the.
Okay, while you're doing it, maybe also Andrew or you do you know about because there's not many SysML open source editors out there. I followed once a project called Topcased. I'm not sure if this is still active, but this was also Eclipse based. But Topcased. Yeah. It seems
Was it
top
called?
case was top case. Yeah, it seems that case like a case, good case, and then ed. So it seems like this one was abandoned, and Papyrus is now the default. So you're going the right way. Okay, do we have some more questions? Because this is also model-based system engineering, right? And SysML is one of the many, or not many, but one of the languages to use for model-based system engineering. Jan Peter, he's mentioned this also in the committee chat. They want to even open a chat group on this. So, yeah, what's the difference between UML and SysML?
It's.
That sounds a bit like teacher questions.
Feedback.
Exactly. You're getting points for the right answer.
But it's a good question.
What? It's an actual. Okay.
Okay. So the difference is slight. SysML is based on UML. Some of the diagrams are exceedingly similar. The behaviors, state machine, like these white diagrams are all the same. The requirement parametric, these are brand new ones, and then a couple other ones just modified slightly. If you can see them well, this is an example of requirements.
Yeah.
And this is a definition.
Okay. Your audio is breaking up a bit, but I summarized that SysML is really just a subset of UML. UML being the language to define software. SysML is language to define systems in the world. So systems and everything is just a subset of software, more or less, right? So that's how we can understand it. Yeah, any more question here? How does Papyrus compare to Capella? Okay, there's another MBSE tool focused on.
Capella's a good tool from what I've seen. I haven't looked into it extensively, but I haven't thought about maybe doing something similar with Capella after I finish the role with system. It uses a different method to accomplish.
Okay. One more question from my side, because the SysML is, well, it's to support model-based system engineering. So it's model-based. It has a model, and everyone works on this same model. So it should be a centralized model, or the model should be synced with each other so that everyone works on the same thing. How does this work out in practice? Because you're starting this Papyrus application, you work on it, but then how do you share it or collaborate with others?
So this is something I haven't figured out how to make it work, but there is supposedly a built-in way to manage the project via a. What I've been doing, just saving everything to a specified folder and uploading that to GitHub manually.
Yeah.
Okay. Also, Red can say something.
Yeah. It's ask the question about Capella too, and I actually don't know Capella much. I just know that it covers some MBSE needs at ESA. So actually, Thales open source that. So it's pretty nice that they did that. And I think on the dimension of a Cubesat mission, you can use one tool, and everybody uses that tool. You exchange the file, and and that's quite okay. But on the bigger dimension, you have different contractors, they have different tools. So what's happening, pushing forward, what's happening at the moment is that ESA is working on a data hub. This is actually a universal translator of all those tools to exchange data and information around that. Yeah, cool. But thanks for the introduction to Papyrus. I've totally forgot about Papyrus. I looked at it a long time ago. And I think Jan Peter can say more about that data hub if you want to know more. Yeah. System Factory, that's the project that is on. Yeah.
Yes. Unfortunately, we have to keep the schedule. So I see now we're getting more and more questions. Luckily, Jan Peter is going to open a dedicated chat channel on model-based system engineering, also SysML topics, and even podcast. So Jan Peter, once you have the link, you can put it here in the chat for Risto also to join. And our next and
thank you, Risto. Thanks a lot.
Thanks. And our next and really last speaker of today is Daniel. And yeah, he is he's a research fellow in the metadata architecture at the Harvard Smithsonian Center for Astrophysics. And he's currently leading the Metasat project. So he's really the person to go to know about Metasat. So he's going to share with us what he's done over these years. He's given a talk last year as well. And he's working actively together with LibreSpace Foundation. And outside of Metasat, he's also an active member in the software citation and attribution community. A very important point. In particular, in Germany, there's a number of politicians. They had to step back because they did not do a proper citation of their sources. So they should have contacted you for advice beforehand. But now we are going to hear from you about Metasat. So the floor is yours. You have 12 minutes, and then we have some Q&As.
Great. Well, thanks so much for having me. I feel honored to be the last presentation for today. So a lot of you are probably already familiar with Metasat. I've been talking to you all for a few years now, and so I know some of you may know what the project is already. But I'll start with a brief introduction on what it is for those who don't know. And so, yeah, Metasat is a metadata toolkit specifically for small satellite missions. So it's used to describe all aspects of a satellite mission. So that includes the ground segment, the space segment, the launch segment, and some parts of what we're calling the user segment. And so there's a lot of bells and whistles to Metasat, but primarily its main focus is on its metadata vocabulary. And that is a list of over, I think it's over close to 1,500 terms now that are used to describe those segments that I just mentioned. So let me just change this. Yeah, so the issue that spawned the idea of Metasat was just, as I'm sure everyone is well aware, is the massive proliferation of small satellite missions. And with these missions comes tons and tons of data, different types of hardware, different types of software, and lots of resources from both prior to the mission, during the mission, and after the mission. So resources such as different forms of documentation, like lessons learned documentation, all sorts of different data sets and things like that. So how do we organize all of this information? And what could we use to tag things? How do we structure them? And so that was the genesis for Metasat, was trying to address that issue in particular. So like I mentioned, Metasat is tailored towards linking all of these things together. And so our website, or also our database, can be accessed at schema.space and then /Metasat. That's how you get to our vocabulary itself. So it is completely open and collaboratively developed. So, as someone without background in any sort of spacecraft engineering, or I haven't had any involvement in space missions before, we have created the entire content based on user feedback. And so our friends over at LSF and SatDogs have provided a massive amount, but also different universities and actual missions. NASA is involved, and so a lot of different groups have contributed to this toolkit. So if you were to go to that link that I had there, it would bring you to our concepts page. And so I mentioned earlier that we've broken it down into segments, but we also have broken those segments down into individual, what we're calling concept families. So concept is a term. It's just another way of saying term. It also could be understood as a key in a way. So yeah, a family is just a narrower way of looking at a segment. So for example, under the space segment, we have families for each individual subsystem. So we have an attitude control family, we have a thermal control family, propulsion, electrical, all those different kinds of things. And so it's just a way of looking at the terms and organizing them, but it's by no means perfect, and there's a lot of overlap between different families. So all of these terms in the vocabulary are both human readable and machine readable, and we accomplished the machine readable part through creating minting URIs for every one of our concepts, every one of our terms. And a URI is pretty much, it's very similar to a URL, and it's just a way for machines to find a resource and to dig into it further. So our URIs, for example, for each term has what we call a crosswalk to other existing standards and vocabularies. So that means that, let's say you use our term for, I think, thermal control, you'll be brought, so let's say you use that in your own database. The URI to our database will bring up all the information that you see on this slide. So it will include a description, an example, if there is available, a synonym, so this is a big part, and then also the segments and families. So you'll see for gravity, it's very similar. This one has an example value. But going back to the crosswalk, so at the bottom of this page, you'll see all the different existing standards and vocabularies that we have crosswalked to. And so this means that if you use one term in your database or API or website, that it's semantically linked through Metasat to other sources. And so that, let's say I have a database in Japanese, if I use a Metasat URI, that could resolve to an English page by virtue of, let's say, a crosswalk to Wikidata. So Wikidata has plenty of actual translations in it. So it's just a way of linking together a bunch of different and often sometimes competing databases so that everyone is speaking the same language. And so here you can see the Wikidata page for gravity. This would be something that we would link to just as an example. And you can see how it has a Spanish translation, the Chinese, traditional Chinese, and stuff like that. So these URIs are tailored specifically to be used in the JSON-LD data format. So JSON-LD is just a different serialization of JSON, regular JSON, for just optimized for link data. What that is you can see at the very top here, there's an @context feature in JSON-LD. And with that, that's where we're able to import those crosswalks that I had showed you earlier. And so you can see, so this is that @vocabulary part right here is it resolves to our website. So that resolves to pretty much every single other crosswalk that we've created. So you can use other people's terms throughout the course of this file just by virtue of linking it out to Metasat. And then in this file, you can see we're able to rearrange or arrange terms given whatever order we want. So this is just an example for a mission that is operated out of our facility, the Minx mission. It's just a description of it, it's very basic. This is just an example file, but you can see how we have terms for NORAD ID, we have things like service life, we have orbital elements, and stuff like that. And so what you could use these files for tons of different things. So LSF, so SatDogs uses it to organize their databases, or at least to be used in their API. But they also could be used in things like search engine optimization. And so you could put these in the header of your HTML files of your websites, and then that can be used to inform Google's knowledge graph of what the content of your page has. And so that is useful. Let's say you search Google for a synonym of a term. Through this file, Metasat can make sure that that synonym is brought up as identified as being relevant to your particular website page. And so we have a couple partners. I mentioned SatDogs already. So that has been amazing working with them. We also are involved with NASA's Small Satellite Virtual Institute. That has been also fun. There's a bunch of different collaborators in that. And so we're working on integrating Metasat within the Small Parts on Orbit Now database, in addition to things like their federated search system, TechPort, and just different databases, connecting them all together. Because Metasat is kind of like a glue of sorts. You can kind of connect all of these different sources, make sure that we're on the same page. And then the last one, well, not the last, but the most recent, is the Small Satellite Reliability Initiative. So this is an offshoot of S3VI, and they're working on, if you're not familiar, a massive knowledge base. So something similar to Wikidata, actually, but just for organizing things like lessons learned for small satellite missions. And so Metasat is now partnered with them. And so we're using Metasat to create their glossary, in addition to using Metasat terms as tags for their search engine. So when you search for a tag in the new knowledge base, if it matches a Metasat tag, then it will result in a bunch of papers relevant to what your search was for. And then, so this is the thing that I wanted to talk about most today, because we're looking to start a steering committee for Metasat. So like I mentioned, it's an openly developed toolkit, and we want to create some more concrete ways of moving forward as far as informing our development and creating a new form of governance. And so we would like for people who are interested, you could reach out to me. At the end of the slide, I'll have contact information if you're interested in joining the steering committee. We're trying to get as many voices in as possible. But it's going to be very informal and just a way of us deciding what we should work on next, and what are we doing right, what are we doing wrong, how is our content, what else can we link on to, what other use cases do we have. And so that is one of the things that we're looking to do in the future. So that would also inform our new release cycle, which uses semantic versioning at the present moment. So the other thing that we're working on is a new JSON-LD generator. So on our website, you'll have a page. We're going to have a page soon that you could just fill out information about your space mission, for example, and it'll spit out one of those JSON-LD files that I showed you earlier. We're working on creating RDF serializations for all of our terms. So that's the resource description framework. So that would just be something similar to JSON-LD files, but just for more broad applications. We want to create an API soon. That is something that I'm very excited for. I mentioned earlier, so we're working on faceted search and SEO related things. And then, as always, community-driven development. And so here is my contact information. There's my website, and we have a GitLab repo, which is where all the hard and heavy work is done. So thanks.
Thank you, Daniel.
Yes.
Yes. Meta. Good. So we still have a bit of time left for a number of questions. So keep those questions coming in. I throw one in. I was pleased to see that you're using JSON instead of XML. Yeah. It was very good.
Yeah, me too.
Decision for human readers. So I have read a thing. I have a cube, but I'm letting Patrick ask this. Oh, don't get it?
Yeah, this is a way to put Patrick on the spot, but maybe he has no questions.
Okay.
I have, yeah, it was like, how do you get started when you have a mission? That's my question. And also, I'm taking the example of the Polaris project for which I contribute. So we use the data from other spacecraft, and would you love to add some semantics to it? And how do we do that? How do we start?
Yeah, I mean, that's a great question. I think it really depends on what you're trying to do, right? And so right now, we're experimenting with ideas of different ways of applying Metasat to knowledge management systems. So trying to capture missions from beginning to end through, let's say, these JSON-LD files that would inform a database on all of your materials associated with the mission. So that is one possible route. Yeah, it really depends on what you like to do. If you already have, let's say, if you're involved with another organization, you want to make sure that your terms that are used to describe your spacecraft match with theirs. There's that. I realize that when it comes to space missions, there's almost never just one organization involved or one team involved. There's always a lot of different people working on a project, and so this could be used as a way to connect all of them just by virtue of everyone speaking the same language, so to speak.
Yeah, I have actually I had exactly the same question like Red, so I'm not going to ask the same question. So I refined it a bit. I was wondering that if we think about Wikipedia or Wikidata, people contributing with their information and even trying to stick to your syntax, but still, well, at least in Wikipedia, there's some moderation going on to make sure that this information is actually factual and not just made up. So, what is your plan on this? Are you going to have some like post moderation checking?
Yes, yeah. So this is a problem I think with faced by a lot of open projects. Is we just need to make sure that the content in our database is valid and accurate. So one thing that we're envisioning with the steering committee is to have subject experts, and so I've already reached out to a couple of different people. For example, someone I know who is very blockchain consensus. Yeah, it's an idea. Sorry. Yeah. So we were thinking about. I have someone in mind for propulsion systems, for example, stuff like that. But I don't know. It's kind of an issue that we need to address more, and I'm open to have a conversation on that. I definitely want as many voices in as possible. And the one thing I'm hesitant about when it comes to subject experts is that if it's only their voice is being heard. So I'd like to make sure that we have consensus between everyone.
Okay.
So, I feel like there's a common answer to the previous one is you have to involve people. That's
yeah, exactly.
Okay.
Yeah. And I see in the chat, Patrick had mentioned KMT as units in the JSON-LD file. So that is a Unicode. So we in JSON-LD you could use Unicodes. I think what's the name of the organization that makes them? It's involved with the United Nations. They have a set of Unicodes, and so we use those in our JSON-LD files to make sure that units are consistent. Hi, heroes.
Yeah, talking about codes and formats, I realized that the state formats that you used, they were like just plain as we write on a letter. I mean like 9th of June or something, but would you not consider to use some kind of more parsable format like ISO format?
Yes, absolutely.
Or
yeah.
Can everything be parsed?
So you're referring to like the examples in like the database, those values, or in a JSON-LD file. So the values that we have in our database, for example, are just strings. They're not semantic. They are just actually those values are purely for user friendliness, just so you could get an idea of where this concept would be used. So those don't have any semantic meaning. I would like them to, and I could envision us using something like an ISO standard or something for that, or Unicode, for example. When you actually implement these terms in a file or a database or something like that, that's when you could really get more precise and use like Unicodes. If you're using JSON-LD, for example, it's very easy.
Okay, thank you. Also, Pieros is mentioning you, applauding your talk in the chat. And good. That brings us to the end of the last session. And it's interesting to see that in your window, the sun is shining.
Yes.
Here, it's already disappeared. So the sun is now on your side of the world.
Yeah, Massachusetts, it was snowing here before, so it's getting quite cold. But thank you so much for your time.
Oh, snowing. Good. So, Lutz, the last yeah, you have a break after the closing. I think, do you have some more lightning talks?
Oh, sorry, I was muted. I was saying you were breaking up. I could not hear you.
I'm breaking up?
Yeah, it's better now. Yeah.
Okay. Yeah, I see my bandwidth is red. Now it's green.
No, it's good. It's good. I think you asked if I had more lightning talks. The answer is no. No more emails on my side. Thank you, Glenn. Yeah, we're wrapping up. We have some wrap-up points, right? But first, before we do that, we're 35. I think we can have a big yes for the whole conference. So you have, as the lightning talk rule, you have 3 seconds to unmute and say a big yes. 3, 2, 1.
Yes!
Yay!
That was awesome. Thank you for the opportunity.
Yeah, that's nice. So Arthur, can you guide us to the closing points?
Yeah. Okay, so first thing to do, group picture. Let's stress the server a bit. Everyone, camera on.
Turn on your camera. Come on, Adrian, Agis, Abdelmunan, Andrew, Danielle. We know you have a camera. Nice. Frederic Rab, yeah. Everybody, Konstantina, Yak, Manolis. You're here already. Can you turn off the presentation? Oh, it's okay. You can reduce the presentation. Nice. You go back to Azilis.
You cannot disable the presentation, but I minimized it.
Yeah.
So when you can minimize the presentation. Wow. Now the server is really busy.
I want to give a special thank to Vasilis, who actually helped us audio connecting people, because some of you that could not connect because we have a new domain. So in some VPNs it's blocked, in some for some traffic flux. And Vasilis actually was this satellite orbiting with Mumble, and through his laptop, wherever he's in Greece, he redirected the audio of people. And in and out. This is crazy. Thanks a lot.
So it's
and thanks everybody. Yeah, Glenn.
Also.
Yeah.
On the west coast of the U.S.
Yeah.
Okay, so 3. Oh, there's more people coming. Good.
Turn on the camera.
Red, you're doing the countdown, okay?
Okay, I'm doing the countdown with my fingers. Are you ready? Make your best face for open source CubeSat workshop at 3, 2, 1. Is it a good one?
People are just switching on the camera after the picture. Come on.
Okay, once again. Everybody get closer together. I mean, squeeze the windows.
Come on, everyone, come on stage.
Perfect, yeah. Great. Okay, we're doing
No rush.
Again. Are you ready?
No rush.
No rush?
Take your time.
Take your time. It's like a real conference. But that in the real conference you can.
We need one more.
The one next to you. It's different. So okay, let's take one. Arthur, you're frozen. It's good. We take a picture with Arthur frozen. You can take the picture. Pieros, you take the picture. All right. 3, 2, 1. Your best face. 1. He's taking the picture. I see you, Piotr. Yeah, I'm ready. Very good. Okay, Arthur just left, unfortunately, but we've got his frozen picture, I think, in this one. Arthur, are you back?
Yeah.
Yeah.
I think so.
Yeah. There's always one which does a bad face or just go out because, getting the phone or whatever. And Arthur is that guy. He's coming back. Can you turn on your camera again, Arthur, or we lost you totally?
It should be on. I can see myself, but
you can see me. I see you. I didn't know where you were. Okay, another last one. Okay, guys, are you ready? This is Frederick. Good. I see you. Okay, cool. You're beautiful, Basil. It's perfect. Okay, ready? Adrian, the same. It's perfect. Adrian, the same face. It's perfect. 3, 2, 1.
Yay.
Am I right? Perfect. Good.
That's fine.
Sebastian.
cool. I've taken about 10 pictures.
Okay.
So we can photomorph them into one and
yeah.
Or use some face detection algorithm or whatever.
And detect where's Glenn. Okay.
To use the AI to find out how many cats were actually in the picture.
That's a good one.
Good.
In the tree.
So you can.
How many trees? Yeah, like Glenn has in his face. Cool. So some highlights now.
Everyone sees the presentation. Yeah, you can put large again. You can also use a text modus. So just feel free to jot down any kind of thoughts like.
Use the text.
Just uploaded 2 of the pictures.
So I just
on the copy.
That.
Like keywords of the thing that haircut of Pios. Mantos, you have a haircut as well. Oh wow, okay. Just use my haircut, it's the best. Oh yeah. Can speak up. What's your highlight?
There's also a text tool, so you don't have to use. Okay, you can find it out.
I think for me, it's IPFS Tiny. I love that project. That is writing in blue. I think we had a lot of things. Lightning talk, yes. Did you like the yes? I think we should do only lightning talks and engage in discussions.
Lightning talks are really great. You can really feel the pressure and the excitement of these 4 minutes that you have.
I'm actually interested in, Glenn, did you feel the pressure on the lightning talks, even if you were not in lightning talks? You, Adrian?
The pressure is higher when you're on stage, though.
Yeah, I don't know.
Because if you don't finish in time, someone will escort you from the stage. 2 big people will do that.
The bouncers.
One from each USB port.
USB teleport. Aries. You're on YouTube. Yeah, good. Okay. Yeah, space education. I see. I put my +1 also over there. I think the project from Michael Turner, which is I'm not sure it was too clear, but the thing is that after the 2017 problems in Malawi, Philippines, is trying to bring communities together through educational and space projects. That's pretty nice. So yeah, big thumb ups to his project. His project is called Perse. Oh, it's complicated. Michael Turner.
Perseus.
Perseus, yeah. Check it out in the timetable on the lightning talks. Interesting, yeah.
Cool. I'm also interested to get a model of the Kronos rocket.
Yeah, Thanos, come on.
Would you send it over to Germany? I mean, via DHL or so?
Did you open
I thought that you meant flight actually from Greece to Germany. I mean, that didn't work out. That didn't work out really well in the past.
Are you sure you have no fly zones somewhere? Or it's, go above the no fly zone?
Okay. Next slide.
Yeah.
So the workshop, I think there's been good stuff and maybe not so good stuff. Also, we are really open to hear any kind of comments to further improve the workshop. So if you liked something particular, you can mention it here.
Okay.
I actually don't like being the organizer of that workshop. Would love to be a participant.
So I make this point every time, and we'll continue to do so. We need more diversity in the audience, but potentially also in the committee. It'd be good to see some new faces.
Yeah.
So if you're interested, well, if you say you don't have time, then I can tell you nobody has. So
we manage. So, but there's a topic is that because we've done it several times, with Pieros, you, Elkos, myself, we kind of don't have an issue list. We just go, and it's not good, but we manage. It's not good because sometimes.
I mean, it's amazing how little we had absolute planning over.
Yeah.
I mean, we just knew whatever everyone needed to do, and we just did it. So that works out pretty well. Which I don't think that's going to be the case for the next. Like if it's a virtual again, hopefully not. Then yes, okay, that's going to be fine again. But if it's a physical one, then that means that there needs to be a lot of knowledge transfer, unless they were like,
okay.
done in education that is done before.
It's all well documented, and let's say the other way around. We start from scratch every time. So.
No, but for the on-site, it's actually well documented. So we have the time still. Yeah.
I'm just trying to not scare away the people. So.
Yeah. Another thing is what I wanted to finish on is that if you want to join, I'll be there for you. It's just that you will roll when the open source Cubesat workshop will start. and you won't need us anymore at that moment, hopefully. But it's not difficult. I mean, it's not difficult. The people, I mean, the community is amazing, so the interactions are super nice. You also get to know a lot of people and projects, you know, before they're shown. So it's really nice. Yeah. But what I wanted to, okay, you know, I wanted to make a suggestion is that we next year we aim at on site somewhere, but we keep one remote, or actually 2 remote, but just half a day or a full day, not 2 days. You know what I mean?
No.
As for, you know, courses on Coursera, they are like 5 minutes videos. It makes them, you know, you get to the next thing. So, but looking for a shorter version of OSCW on remote. What do you think?
I mean, I like really much this this aspect of being live. And if you I mean, there was this one exception with Michelle to show a video, but even that was totally fine because she was there in the chat. She was there with us, and I think this is really the feeling that makes the difference. That I've seen other online conferences where they schedule to run videos at certain times, but I always felt really passive, and I didn't even know. I mean, it would have made no difference if I'm there or not. And so that's the aspect I really like. Of course, physical presence is not replaceable, but to be here at the same time and to see each other and to know that it's live, I think that's really helps to keep this community spirit.
I absolutely agree with what you're saying. My experience was the live aspect made the presentation more challenging and more rewarding at the same time, because I see, you know, there's 34 people from all over the world watching this, and then it's being recorded onto a YouTube, which will be laying out there on the internet forever. You got to get it right in real time, and that's really good. I sincerely appreciate the virtual aspect. I think I commented on this page here, which is getting pretty crazy. Having it virtual like this meant that we were able to bring in 5 students from North America without having to incur all the travel expenses and all that kind of stuff. Now, being in person is absolutely wonderful. I know Polaris has mentioned to Andrew and to other people in our group, oh, come do this, and we're like looking at each other and thinking, how are we going to afford that and still build a satellite? Because every dollar we have goes into our project, and every minute of our day goes into solving problems. And so this actually was amazingly timed. We had just handed off Orsat like the week before, and Andrew said, oh, we've got to do this. And I'm like, well, we probably can do this. And we pulled it off to some degree. So thank you. I like the virtual aspect, or at least having that as a yeah, thank you. Awesome. At least having that as a as an option.
I think we'll keep it, whatever happens. I think.
Yeah, we can always, even for the you know, in the event that we're gonna have like a physical meeting, we can always have an option for something like a hybrid thing, right? Like where we have like remote presenters. I mean, the technology is there, and you know, probably that's the way to keep the best of both worlds, basically.
A lot of times, so we have weekly meetings on Orsat, and before the pandemic, we did actually have probably 2/3 of the group physically in our lab as a part of the meeting, and then several people on some type of remote communication. In fact, I think that's when we started to use Zoom for the first time. And it did allow us to keep the group more dispersed across the country and across other continents. And that is part of what Orsat is about, that we're really not just limited to those people who can make it to the engineering building on Friday afternoon. And so that aspect, yeah, like what Pierce just said, we have the technology. Let's embrace it sort of as a hybrid. I mean, I'd say from our standpoint, that's what we try to do.
Good. Yeah, Jan-Peter is mentioning something. Okay, work adventure. So I must say that I really like the value of online conferences in the sense that we don't need to travel, and that's very convenient to stay at home. And right now there's no other option. But there's different online tools for that, and in particular for larger conferences where you just have a list of names. I feel a bit still. I mean, I lost my video, but you hear my voice, right?
Yeah.
Yes.
Yeah. So I still feel a bit passive. If you're not presenting, if you're not, have your microphone on and ask some question, you're still a bit passive. So, okay, there's a link that Jan-Peter posted. It's like a 2D version where you walk around and you can communicate. That's already an improvement, I think. But now I have another pet project, which I'm throwing at you right now here in the chat. And that's yet another dimension. That's namely the 3-dimensional conference room in the spirit of Minecraft or Minetest, the open source version. I guess you know that. You can walk around, you can build something with blocks, and you can, and that's what we did. We added some audio so you can actually talk with each other while moving around in a virtual world. And this is a project which is ongoing. You're really invited to join. And maybe that's going to be the platform for next year. Let's see. Okay, so Red, you were already... Sorry, Glenn, yeah.
Oh, no, I was just going to say, you put up a slide with the Earth on it. Were we going to check where we are on the globe?
Well, the next slide was, for... we can do it for two rounds. One would be, as you say, where we are. But it's also for to decide where's the next non-virtual conference. Where would be your preferred location once we go physical?
Actually, a question for you, Glenn, in parallel.
Yeah.
Is there a best time where, student projects needs to be presented or could be presented, they reach some kind of maturity where it's nice to share in the presentation?
You mean a time in the life of the project, or
yeah, or more time in the year? Like, did you observe?
Yeah, that's a good question. I see Andrew popping in and out here. He's probably the best person to answer that question.
Yeah, the best time for student projects is always end of break, and so it would be like right next week would have been optimal for us because it's be after final exams. Same thing with late summer. The problem is that all the schools have different times, and so it's really hard to pick an optimal time for academics. But right before winter break is probably the optimal time, because most folks take off, the second or third week in December.
Yeah. Okay. Noted. Thanks.
I've always wanted to go to Antarctica. Does that count? Can we do that?
Yeah. I mean, that counts. Everything counts.
OSCW McMurdo.
I suggested Chile or Iceland. I guess I'm a little off on the map for Chile. It's just right about here, right?
The pen. China. I put China, guys.
Since it'd be great to have a North American one, but that's since most folks are from Europe. I think the timing of this worked out well, where the North American folks came in early in the morning, as you guys were cleaning up the day. I think that makes sense. That worked out well for us, and then we just go back and listen to the YouTube stream. Thank you for streaming it to YouTube.
No, don't worry, Andrew. I mean, once we have it in the US, it means there will be a lot of US participants, and for us Europeans, it's absolutely no problem to burn the midnight oil. I mean, we really love to do that. That's hackerspace mentality.
Yeah. Also, just for your information, we had planned it on the East Coast just before the pandemic, and we canceled. It was actually with the Center for Astrophysics, the Smithsonian. Nice. Yeah. With David Chivas and Dinah Boucan, and fortunately we could not make it. Yeah. The room was booked. Yeah. I think Aris and Thanos are making signs, like Scandinavia. Thanos was like in the middle of the Atlantic. I think he pointed to Iceland.
Go to the Azores.
And pick a hot place. I mean, that would be nice. Okay. Let's take a picture of that.
Two people are chasing each other around the globe.
Yeah, deactivated for the picture. Thanks. Cool. Costa Rica. Cool.
Is that not in Panama though, right?
Yeah. For the little story, Argentina, they came for the first open source Cubesat workshop. They actually engaged their Ministry of Science and Education to support them. And then they actually wrote a new master degree syllabus for space and development. And they actually kickstart or engaged and motivated the space agency over there. It's kind of nice.
Awesome. Wow.
Yeah. So, and I think Michael Turner wants to do the kind of similar things in the Philippines now. And we've seen Costa Rica here. They already have their space agency, which was started this year. So it's good to see, motivation.
The first edition had quite a lot of far-traveled participants, right? I remember we had one guy from Team Indus from India, one guy from Nepal, 2 from Japan who came over.
Yeah. That was, I think that was a lucky shot, because that year I actually went to Japan, actually met with the team over there. And I don't know, there was the Lunar X Prize momentum. And we had PT scientists from Germany and Team Indus from India. Yeah, that was cool. Yeah, next year we have SpaceX and we unveil all the open source things they're using. That'll be cool, man.
Yeah.
Even cooler if they contributed back.
Yeah, that's even more cool,
Adrian, do you want to say a few words? I've seen you here in the chat. No? Okay. All right. Good. I think we can call it off here. I mean, we can leave the room open if you want to chat a bit more and bring up some emotional stories from the live presence workshops. But for those that maybe need to go to dinner, spend some family time, free to log off, I will do that. And I'm really much looking forward to the next workshop. A year goes by very fast, I realize, and I'm looking forward to the next one, wherever it is, and stay in contact. We have the channel, right? Red?
Yeah,
you might
by
want
the
to
way,
post
that's
some links.
information. Yeah. So we have a channel, like a Slack channel, which is on Matrix. You can access through Element. I'll paste the link here. It's actually where things happen. It's actually a backstage of the workshop. We have discussions with everybody. I'll submit information there. So if you're not there, you're missing out part of the things. But also, like, it helps keeping in touch the whole year somehow. So, yeah.
Well, hopefully we'll have something to report back with Orsat 0.
Oh, you will.
yeah, right.
You will. We hope for the best.
Yeah, absolutely. And that is our next big thing, obviously. And so thank you for the opportunity to partake this year. And we will obviously be here next year. So
awesome.
I will
thank you.
bow out at this point.
Me too.
Unless Andrew had something to say there really quick. I will bow
No,
out.
thanks everyone.
Thank you.
Thanks, Andrew.
Appreciate it.
Everyone.
Bye guys.
Ciao,
Take
man.
care. Talk to you
Have
soon.
a good one. Take care.
Bye-bye.
Ciao.
Thank you.
Yeah!
Merry Christmas.
Yes.
Woohoo!
All right. See you guys.
Ciao. Yeah, Adrian. You raised the hand. You can try anything now. That was nice here. Thank you. I can't hear you. Sorry. Trying to read your lips.